Hello there, and welcome to Physics with William. Where curiosity slows down a little, the universe gets comfortable, and even the strangest ideas in science are allowed to unfold at a pace that does not demand very much from you at all. Tonight, we're settling in with something that seems familiar on the surface, and yet becomes deeply odd the moment you look at it closely. Gravity. That dependable thing that keeps your feet on the floor, your tea in the cup, and your phone from floating off into the corner of the room like it has suddenly decided it prefers the ceiling. It feels obvious. It feels settled. It feels like one of those subjects that was wrapped up long ago and tucked neatly into the drawer, labelled basic facts about reality. And yet gravity, as it turns out, is one of those ideas that looks simple only from a distance. The closer you get, the stranger it becomes. Most of us grow up with a very straightforward picture. Gravity pulls things down. Apples fall from trees. Keys slip from pockets. Rain comes down rather than drifting politely sideways. If you jump, you come back. If you drop a spoon, it does not hover and consider its options. It heads for the floor with great determination. It all seems quite sensible. And for everyday life, that simple description does the job nicely. You do not need a deep theory of space-time curvature to know why your toast will not remain suspended over the breakfast table. Gravity appears to be the most ordinary thing in the world, almost boring in its reliability. In fact, one of the reasons it is so interesting is precisely because it hides its weirdness so well. Before we get into that though, I would love to know where in the world you're listening from tonight and what sort of hour has found you. Is it late evening where you are, with the room beginning to quiet down and the day finally loosening its grip? Or is it one of those early morning moments when everything feels slightly unreal and the coffee has not yet had its say? Perhaps you're listening from a city apartment with the low murmur of traffic outside, or from somewhere quieter where the only sound is the occasional creak of the house settling into itself. Wherever you are, and whenever you are, I am very glad you are here. And if you find this little journey relaxing, interesting, or simply a pleasant way to let your mind drift somewhere unusual for a while, I would be ever so grateful if you gave the video a like and perhaps subscribed as well. It helps this quiet corner of science find other people who might enjoy a slower look at the world. Though I should probably add the usual warning that I do hope this is soothing enough to help you unwind, and not so intriguing that you suddenly find yourself wide awake at 2 a.m, staring at the ceiling and wondering whether the floor is, in a sense, pushing you upward all night long. Because tonight, I am afraid, that is exactly the sort of trouble we're getting into, so settle in, get comfortable, and let us start with a small shift in perspective. Not a dramatic one at first, just enough to make the ordinary feel a little less settled than it did a moment ago. When you think of gravity, the most natural image is usually some kind of pull, an invisible tug, a force reaching out from the earth and drawing everything downward. It is such a natural picture that it hardly seems worth questioning. Down is down. Heavy things fall. Your body has weight because the planet is pulling on it. Case closed. Except that the deeper story tells us something rather different. Not different in the sense that apples stop falling or chairs suddenly become optional. Different in the sense that what you think is happening may not be what is actually happening at all. To see why, it helps to begin with something you have probably felt many times without giving it much thought. Imagine missing a step on the stairs. Nothing serious, just that brief unpleasant little drop when your foot expects the floor to be there and discovers it has, for the moment, other plans. In that instant, there is a peculiar sensation, a kind of weightless lurch, as if your stomach is attempting to file a complaint. Or think of the moment a lift begins to descend, that brief feeling that something in your body has gone slightly light. Or the top of a roller coaster, when for a second your body seems less committed to the seat than it was a moment before. These experiences are small and perfectly normal, but they contain a clue. Because what you are feeling there is not gravity becoming stronger or weaker in any ordinary sense. What you are feeling is a change in support. That distinction matters more than it first appears. We tend to assume that weight is what gravity feels like, but according to Einstein's view, what you actually feel as weight is not gravity pulling you down. It is the floor, or the chair, or the bed, or the ground pushing you up and preventing you from doing something very natural, namely, falling freely. Now that sounds backwards, and perhaps a little rude, because many of us have had years of experience standing on the earth without feeling particularly as though we are being shoved around by the furniture. But this is where gravity begins to depart from common sense. In Einstein's picture, an object in free fall is not being battered by some force in the way a shopping trolley gets pushed across a car park. It is simply following its natural path through curved space-time. That is the remarkable claim. The falling object is doing the simplest thing available to it. The one in trouble, strangely enough, is the one standing still. Take a moment with that, because it is one of the most important reversals in modern physics. If you drop a ball from your hand, your everyday instinct says the ball has started to experience gravity and is now being pulled downward. But Einstein invites us to see it differently. The ball, once released, is no longer being held off its natural path. It begins moving the way space-time itself tells it to move. It is not the ball that has suddenly become abnormal. It is your hand, moments earlier, that was interfering. And when you are standing upright on the earth, perfectly motionless by ordinary standards, you are not simply resting in some neutral state. You are being continuously prevented from following your own natural free-falling path. The ground is doing that. The ground is the thing exerting the pressure. The sensation you call weight is that pressure. This is one of those ideas that can sound almost like a linguistic trick at first, as though physicists have merely chosen an eccentric way of describing the same old thing. But it goes much deeper than wording. It changes what gravity is. It changes what motion is. It changes what counts as moving naturally in the first place. For a very long time, the most successful description of gravity came from Isaac Newton, and it was magnificent. Newton gave us a universe in which masses attract one another. The Earth pulls on the moon pulls on the Earth, the sun holds the planets in their paths, and the same force that brings an apple down from a tree also guides the motions of the heavens. It was elegant, powerful, and astonishingly effective. It united falling apples and orbiting planets in one grand framework. That alone was a triumph of the highest order. Before Newton, the sky and the earth had often seemed like separate realms governed by separate rules. Newton said no, the same gravity works everywhere. One set of principles, one universe. It is hard to overstate how extraordinary that was. And for most everyday purposes, Newton remains superb. Bridges do not collapse because engineers have abandoned him. Satellites do not lose their way because his ideas were foolish. Quite the opposite. If you want to calculate a great many things in ordinary conditions, Newton serves you very well indeed. He is not wrong in the casual sense. He is just not telling the deepest version of the story. Rather like saying that the earth is flat enough for building a garden shed. For the shed, yes. For the planet, not quite. Newton imagined gravity as a force acting across space between masses. A pull, you here, planet there, and between the two an attraction. That picture feels intuitive because forces are the sort of things we know how to imagine. We push doors, we pull drawers, we drag suitcases. We can picture one thing affecting another. Yet even in Newton's time there was something a little unsettling about gravity. How exactly does one object reach across empty space and tug on another? What is doing the tugging? Newton himself was not entirely pleased by the mystery. The mathematics worked beautifully, but the mechanism remained elusive. Then, centuries later, Einstein arrived and proposed something far more strange and, in its own way, more satisfying. Gravity, he said, is not best understood as a conventional force at all. Instead, mass and energy change the geometry of space-time itself. They shape the very stage on which motion happens, and once space-time is curved, what counts as straight motion changes with it. That phrase can sound dense at first, but the basic idea is more approachable than it may seem. Imagine you're walking across a perfectly flat open field. The straightest path is simple enough. You keep going forward, Now imagine the ground beneath you is no longer flat, but curved and sloped and shaped in ways you may not immediately notice. The path that feels straight locally may lead somewhere unexpected when viewed from a distance. In curved terrain, straight does not always look straight in the old familiar sense. Einstein's claim is that space-time itself behaves like that. Massive objects do not simply sit inside space and pull on things, they alter the geometry, they change the paths available. So when the Earth moves around the Sun, it is not, in Einstein's view, being yanked around by an invisible rope. It is following the natural path laid out by the curved space-time around the Sun. When the Moon circles the Earth, it is doing the same. When you drop your keys, they are not just being pulled downward in the old picture of a force reaching out and dragging them. They are following the path space-time offers near the Earth. The reason those paths head inward rather than out into the kitchen window has to do with the shape of space-time around a massive body. And here is where the story becomes even more interesting, because space-time is not just space, it includes time as well. We often talk as though space and time are separate things, and for daily life that is usually fine. You ask where something is and when something happens, and those seem like different questions, but in relativity they belong together. Space and time form one connected structure. That means gravity is not only about where things move, it is also about how time passes. This is one of the least intuitive parts of the story and one of the most important. Near a massive object, time itself runs differently. Not metaphorically, not psychologically in the way a dull meeting can make 5 minutes feel like a geological epoch, but physically. Clocks in stronger gravitational fields tick differently from clocks farther away. The presence of mass affects the flow of time, and once you accept that, the whole picture of gravity becomes richer and stranger. Falling is not just a spatial matter. Motion through time is involved as well. The path an object follows through space-time includes both where it goes and how its clock advances along the way. This is why gravity cannot be reduced to a simple downward pull in the everyday sense. Downward is not a universal cosmic direction. It is local. What matters more deeply is how space-time is shaped. That shape tells objects how to move. Or more carefully, it tells them what moving naturally even means in a given region. You can begin to see the consequences everywhere once you start looking. Planets orbit. Light bends near stars. Time shifts near massive bodies. Tides stretch oceans because gravity is not identical from one place to another. Tiny corrections must be made to satellite systems because clocks in orbit and clocks on the ground do not stay in step by themselves. Entire ripples in space-time, called gravitational waves, pass through the universe when enormous masses move violently, and we have learned how to detect them. All of these are part of the same broad picture. Gravity is not merely a thing objects do to each other. It is something built into the geometry of reality. Even so, for all its grandeur, the strange truth about gravity can be felt in something as simple as sitting in a chair. Right now, if you're seated or lying down, it may seem that nothing especially dramatic is occurring. You are at rest, quiet, supported. But from Einstein's point of view, the surface beneath you is doing an active job. It is stopping you from following the path you would otherwise take through space-time. You feel that interruption as pressure. If the support vanished, you would not suddenly begin to feel some new mysterious downward force in the way one feels a shove in the back. In a sense, you would feel less. That is what makes free fall so peculiar. The one who feels no force may be the one moving most naturally of all. Astronauts in orbit offer a striking example. People often say they are beyond gravity, but that is not really true. Gravity is very much present where they are. In fact, it is precisely gravity that keeps them in orbit. They are continually falling around the Earth. The reason they float is not the absence of gravity, but the absence of support. They, along with their spacecraft, are following free-falling paths together. Nothing is pressing them against the floor in the ordinary way, so they feel weightless. That feeling of weightlessness is not the disappearance of gravity. It is the disappearance of the resisting surface that, here on Earth, keeps reminding you how much you weigh every second of the day. That alone is enough to make the everyday world look slightly different. The simple act of standing becomes a little more strange. Falling becomes less violent in theory, even if still rather unwise in practice. Rest becomes a kind of enforced detour, and the earth beneath your feet becomes not just a large object pulling you down, but a surface continuously preventing you from doing what space-time would otherwise have you do. This is the idea we're going to spend time with. Not rushing it, not turning it into a pile of jargon, just taking it piece by piece until the familiar story of gravity begins to loosen and a more interesting one takes its place. Because once you start from this simple reversal, that the feeling of weight comes from support rather than from gravity itself, many other things begin to fall into place. Why free fall feels weightless, why Einstein replaced force with geometry, why clocks do not agree in strong gravitational fields, why light bends, why Mercury behaved a little too strangely for Newton's picture to be the full one, why modern navigation systems must account for relativity whether they like it or not, and why space-time, which sounds at first like one of those grand and distant physics terms, turns out to have everything to do with the floor under your feet and the chair under your back. So, rather than picture gravity as a kind of cosmic hand reaching down and hauling everything toward the ground, let us begin to entertain a more subtle image. Not mystical, not poetic, just stranger and more precise. The Earth is shaping the space-time around it. Objects near it move according to that shape. Left to themselves, they follow those paths. What interrupts them, what gives rise to the sensation of weight, is not gravity doing something extra, but matter getting in the way. The floor, the chair, the bed, the pavement, all those solid, dependable surfaces that seem so passive, are, from this point of view, busily preventing you from falling freely through the curved space-time around the Earth. And once that thought has had a little time to settle, the next natural question becomes difficult to avoid. If standing still is not as simple as it seems, and if falling is not quite what we thought it was, then what exactly is the natural motion of an object near a massive body, and how did Einstein come to replace Newton's invisible force with the geometry of space-time itself? It is a curious thing, really, that one of the most familiar sensations in ordinary life is also one of the most misunderstood. Weight feels so immediate, so obvious, so completely beyond dispute that we rarely stop to ask what it actually is. You feel it when you stand up after sitting for too long. You feel it in your feet after a long walk, in your back when a bag is too full, in your arms when you hold a sleepy child who somehow weighs twice as much as seems reasonable. You feel it when you lean into a mattress at the end of the day, when a chair supports you at dinner, when the floor meets you every morning with all the quiet firmness of a thing that has no intention of budging. Weight seems plain. It seems like the direct sensation of gravity itself. The Earth is pulling you downward, and what you feel is that pull. That, at least, is the story most of us carry around without much trouble. And yet the deeper story is more peculiar than that. What you feel as weight is not gravity in the way most people imagine. It is not the direct sensation of being tugged downward by the planet. What you actually feel is the resistance to falling. More precisely, you feel the upward push of whatever is stopping you from following your natural path through space-time. The floor beneath your feet, the chair beneath, your back, the bed beneath your shoulders. All of these are doing something active. They are pressing on you. They are preventing you from moving the way gravity alone would let you move. And that pressure, that interruption, that refusal to let you simply fall, is what weight feels like. This is one of those ideas that takes a moment to settle, because every instinct insists on the older story. Gravity pulls downward, so surely the heaviness in your body must be the pull itself. But let us slow that down and look at something simpler. Imagine standing on a bathroom scale. It is not the most glamorous piece of household equipment, and it has ruined many mornings with perfectly unnecessary honesty. but it is useful here. What is the scale measuring? We casually say it measures your weight, which is true enough in a practical sense. But how does it do that? It does not peer into the Earth and consult the planet about how hard it is attracting you. It does not read some secret gravitational signal. What it actually measures is the force with which you press down on it, and, by the same token, the force with which it presses up on you. The scale reading comes from contact, from support, from the fact that the scale is stopping you from falling. That simple point already begins to shift the picture. If weight were merely the direct feeling of gravity pulling you down, then perhaps a scale would be some kind of gravity detector in the purest sense. But it is not. A scale can only measure the force between you and itself. It tells you how hard you are being supported. That is why the reading changes in an accelerating lift. If the lift begins to move upward, you feel heavier. Not because the Earth has suddenly developed stronger feelings about you, but because the floor pushes on you more firmly. If the lift descends and accelerates downward, you feel lighter. Again, not because gravity has lost interest, but because the support force has lessened. In the extreme case, if the lift were to fall freely, the scale would read nothing at all. Not because gravity had vanished, but because both you and the scale would be falling together, and the scale would no longer need to push on you. That is the strange heart of the matter. In free fall, gravity is still present, but weight disappears. It helps to stay with that for a while because it runs so strongly against the grain of everyday language. We say that a falling person is under the force of gravity, and of course, in one useful sense, that is fine. But Einstein asks us to be more careful. A freely falling person does not feel a force in the way a seated person feels the chair under them. The falling person is not being pressed, squeezed, or supported by anything. The seated person is. The standing person is. The one lying in bed is. The one dangling briefly at the top of a roller coaster and then dropping into that odd hollow sensation is experiencing the reduction of support. The support force eases, and the familiar feeling of weight goes with it. That is why so many situations associated with falling produce that unmistakable sensation of lightness. Not comfort, usually, not joy, unless you are a very specific type of roller coaster enthusiast, but lightness. The body is exquisitely sensitive to support and its changes. When the support beneath you weakens suddenly, your internal sense of weight changes immediately. The stomach performs its theatrical little drop, your balance shifts. Something about the world feels briefly unreliable. This is not because gravity has become absent, but because the structures that normally resist your fall are no longer doing their usual work in quite the same way. The same principle explains why astronauts in orbit float. This is often described as zero gravity, but that phrase is misleading. Gravity exists in orbit. It is the very reason the spacecraft stays near Earth rather than wandering off into the black in search of a quieter profession. The astronauts are falling freely around the Earth, and so is the spacecraft. They move together. Since the floor of the spacecraft is not pressing up on them in the way the ground presses up on you right now, they do not feel weight. The gravity is still there. What is missing is support. They are not beyond gravity. They are surrendered to it in the most complete way, following the path it lays out without resistance, and that is precisely why they feel weightless. Now, if you have never been in orbit, which I suspect covers most of us, and perhaps all of us listening right now, there are still many small earthly examples that point in the same direction. Consider jumping from a low step. Just before your feet reach the ground again, there is a brief stretch in which your body is airborne. During that tiny interval, you are in free fall. Gravity has not disappeared. In fact, it is the reason you are moving as you are. But you do not feel the same kind of weight you felt a moment earlier while standing on the step. Then, the moment your feet land, the ground pushes upward strongly, slowing your descent and halting it. That is when the force becomes unmistakable. Your knees absorb it, your muscles respond to it, and your body feels it all at once. The sensation of weight returns with enthusiasm. Or think about lying down. Most people do not describe lying in bed as being pushed upward, which is fair enough because it sounds slightly hostile for a mattress. Yet that is what is happening. The mattress deforms and presses against you. It distributes that force across a broad area, which is why the sensation is gentle, rather than concentrated in your feet, as it is when standing. If the support is well spread out, the body feels relaxed. If it is badly distributed, perhaps by an old sofa that has chosen collapse as its long-term strategy, the pressure becomes uncomfortable. Either way, what you're feeling is not simply gravity itself, but the contact force from the surface that prevents you from moving downward. This is also why people can feel heavier in some positions and lighter in others, even though the gravitational environment has hardly changed at all. A backpack feels burdensome not merely because the Earth pulls on it, but because that pull is transferred to your shoulders through straps that dig in with all the charm of a badly designed medieval harness. A hard chair feels more tiring than a soft one over time, because the support is more concentrated. High heels are famously less forgiving than trainers because they deliver the required support through a much smaller area, which is a remarkably elegant way to make standing still more difficult than it needs to be. In every case, the sensation of weight depends not just on gravity, but on how support is delivered to the body. Once you begin to notice this, daily life fills up with examples. A heavy suitcase is not just a mass being pulled by the earth. It is a handle pulling on your fingers while you try to stop the whole arrangement from moving downward. A child perched on your shoulders is not simply adding more gravity to the evening. They are increasing the support forces your body must manage from the ground up through ankles, knees, hips, and spine. Even sitting at a desk doing absolutely nothing that would impress a sports scientist involves your body quietly responding to a network of support forces every moment. The seat presses upward. The floor presses against your feet. The desk edge may be pushing into your forearms. The world is constantly preventing you from falling, and your body is constantly negotiating the terms. Now, it would be tempting to say that this is merely a matter of physiology, of how surfaces press on bodies. But Einstein's insight makes it something more than that. It is not only that contact forces cause sensations, it is that these contact forces are what distinguish supported motion from natural gravitational motion. Left to itself, an object near Earth does not need a force in the ordinary sense to begin falling. Falling is what it does naturally in curved space-time. The force enters when something prevents that motion. So the deepest surprise is not just that you feel the chair rather than gravity. It is that the chair is the thing disrupting the simpler path. Imagine holding a ball in your hand. It rests there obediently enough, but from the relativistic point of view, both your hand and the ball are in an unusual state. The ball is not following its natural free path because your hand is in the way. You're applying force to it continuously. Release the ball, and it does not suddenly enter an unnatural state of being acted upon. On the contrary, it becomes freer. It follows the path that space-time allows. We call that falling because of how it looks to us, but in Einstein's picture, the supported ball was the constrained one. The released ball is doing the simplest thing available. That reversal can make standing still seem more peculiar than motion. A person floating freely in orbit, or dropping in a lift with no supporting floor beneath them, can in one very important sense be considered unforced. A person standing calmly in a kitchen making toast is continuously subjected to support forces, and since kitchens are rarely discussed as sites of extreme physics, this feels faintly unreasonable. Yet there it is. Standing still on Earth is not a neutral default in the deepest physical sense. It is a state maintained by the surface beneath you, which keeps you from following the freefall path that space-time would otherwise prescribe. This is one reason the equivalence principle was so revolutionary. Einstein realized that there is a profound local similarity between gravity and acceleration. If you are sealed inside a lift and feel pressed to the floor, There are cases in which you cannot immediately tell whether you are in a gravitational field or being accelerated upward through space. The experience of weight comes from being pressed against the floor, not from some direct sensory access to gravity as an abstract entity. In a freely falling lift, you and any loose objects would float relative to one another. Locally, it would resemble the absence of gravity, even though gravity is exactly what is guiding the fall. That thought, simple and radical, helped point Einstein toward a new view in which gravity was no longer treated as an ordinary force, but as a feature of space-time geometry. This has another consequence that is worth noticing. We often think of being at rest as the easy state, the natural one, and motion as something that requires explanation. But in relativity, free motion is the natural state. Resistance to free motion is what needs the push. The ground beneath you is not passively allowing you to exist where you are. It is actively holding you off your geodesic, your natural path through space-time. That word may sound technical, but the idea is simple enough. A geodesic is the path an object follows when nothing is obstructing it. On a flat surface, that would be the straightest path. In curved space-time, the geodesic can look to us like a fall, an orbit, or some other motion shaped by the curvature around mass and energy. The important thing is that free-falling objects follow geodesics. Supported objects do not. They are being pushed away from them, and that brings us back to the feeling of weight. Weight is what it feels like to be denied your geodesic. Not perhaps the catchiest phrase ever whispered over a cup of tea, but remarkably precise. When the ground holds you up, when a chair supports your back, when a scale pushes against your feet, you experience that as weight. If the support vanished and you began to move freely, the feeling would fade. This is why orbiting astronauts float. It is why a dropped object does not strain against itself on the way down. It is why the sensation of heaviness depends on support, acceleration, and contact rather than simply on the presence of a gravitational field. Even the phrase pulling downward can be a little misleading, though it remains useful in ordinary life. It makes gravity sound like a hand reaching out. Einstein's view is subtler. Massive objects shape space-time, and that curved geometry defines the natural motion of bodies and light. The Earth is not merely grabbing you, it is shaping the structure of the world in which your motion takes place. The role of the floor is then to prevent the motion that would otherwise occur, so when you ask what you feel as weight, the answer is not the raw pull of gravity, but the local pressure of matter interrupting free fall. You can even see the logic of this in how the body itself responds. If gravity were directly felt in the ordinary sense, then perhaps floating in orbit would still feel heavy in some hidden way, but it does not. Astronauts feel weightless because there is no support force across their bodies. Here on Earth, your internal tissues are under slight compression because different parts of you are supported and constrained. Stand for long enough and you feel the cumulative effects. Lie down and the distribution changes. Fall freely and those internal support patterns relax. The body notices support and strain. That is what sensation is tracking. Not geometry directly, but the mechanical consequences of being prevented from following it. There is something oddly comforting in this once it becomes familiar. The everyday world, which seemed to sit so neatly inside the old story of downwards pull, becomes a little more interesting without becoming less practical. Chairs remain chairs, floors remain floors. One should still take staircases seriously, but the quiet physical drama of ordinary life becomes easier to appreciate. Every surface that holds you up is participating in the same grand story. Every moment you spend standing still is, in a sense, a managed exception to the free path you would otherwise take. Weight is not the simple signature of gravity alone. It is the sign that something solid is intervening. That does not make Newton useless or ordinary speech wrong. It just means that the deeper layer is different from the first one we learn. Saying that gravity pulls things down is like saying the sun rises. It works well enough for much of life, and no one at breakfast needs a lecture on reference frames before pouring cereal. But once you want the fuller picture, the hidden structure matters. And in that fuller picture, the sensation you call weight belongs less to gravity acting on you than to the world resisting gravity on your behalf. So the next time you settle into a chair or stand waiting for the kettle to boil, it may be worth remembering that your body is not simply sitting there under the influence of a downward pull. It is being supported, shaped, and gently pushed by the surfaces around it. The heaviness in your bones, the pressure in your feet, the reading on a scale, all of it comes from interruption. From the fact that the earth beneath you is not letting you move as freely as space-time would otherwise allow. And once that idea has settled in properly, it opens the door to the next step, because if what feels natural turns out not to be natural at all, then the older picture of gravity as a simple invisible pull begins to look a little too small for the universe that Newton first described so brilliantly. Long before gravity became the bending of space-time, before clocks began to misbehave near massive objects, before light itself was caught curving around stars, there was a simpler, and in many ways astonishingly powerful idea. The universe, according to Isaac Newton, was held together by an invisible pull. Every mass attracted every other mass. The larger the masses, the stronger the attraction. The farther apart they were, the weaker the pull became. With that one idea, Newton did something so impressive that it is difficult to overstate. He took the falling apple and the orbiting moon and said they belong to the same story. That may sound obvious now, mostly because Newton won so thoroughly that his way of seeing the world became the starting point for everyone who came after him. But it was not obvious at the time. For much of human history, the heavens and the earth seemed like different realms. Things on earth fell, broke, rotted, spilled, and generally behaved like objects in a slightly chaotic household. The heavens, by contrast, seemed orderly, regular, and almost untouched by the messiness below. The stars moved with great consistency. The planets wandered in more complicated ways, yes, but they did so with a kind of dignity. The moon came and went in its phases. The sun crossed the sky. It did not feel natural to assume that the same rule governing a dropped stone also governed the motion of the moon. Newton changed that. He showed that the force drawing an apple toward the earth was the same force drawing the moon toward the earth. The reason the moon does not crash into us, he explained, is not because it is exempt from gravity, but because it is moving sideways fast enough that as it falls inward, the earth curves away beneath it. It is perpetually falling and perpetually missing. That idea alone is so elegant that one almost wants to forgive physics for everything else it later did to our sense of reality. It helps to picture how strange and satisfying that must have been. Imagine standing outside on a clear night in the 17th century. You look up and see the moon, steady and pale and seemingly far removed from ordinary earthly business. Then you look down and see an apple drop from a tree, or perhaps more likely something less romantic and more historically plausible, like a tool falling from a workbench. Newton's brilliance was not merely in noticing that both motions involved descent. It was in realizing that one universal rule might account for both. The apple falls to the earth, the moon falls toward the earth. The difference lies in how fast each moves sideways. The apple does not have enough sideways speed to miss the ground for long. The moon does, and suddenly the distance between garden and sky collapses into one coherent picture. That was the triumph of classical gravity. It unified the ordinary and the celestial. It took what looked like separate domains and stitched them together with one invisible force. The same pull that kept your feet on the ground kept the planets in their orbits. The same law that described a tossed stone described the path of a comet. Science loves unification for good reason. It is one thing to explain many things with many rules. It is another to explain many things with one rule. Newton did the latter, and the effect was transformative. What made his picture so compelling was not only that it was broad, but that it was precise. Newtonian gravity was not vague or poetic or merely suggestive. It let people calculate, and calculation in science is where admiration begins to harden into trust. If you can predict where a planet will be, when a comet will return, how a cannonball will arc, or how tides will shift, then your theory is doing more than sounding clever. It is capturing something real about the structure of the world. Newton's theory did that spectacularly well. Sailors, astronomers, engineers, and mathematicians all gained something from it. Navigation improved. Planetary motion became something that could be predicted rather than merely admired. The universe began to look like a great mechanical system, immense and intricate but fundamentally intelligible. If you knew the masses, the positions and the speeds, then in principle you could work out what would happen next. There was a confidence in that view, a sense that nature had yielded one of its grand organising principles. And yet, for all its brilliance, Newton's gravity carried a mystery inside it. It described attraction between masses with extraordinary accuracy, but it did not really tell you what gravity was in any deeper mechanical sense. One object influenced another across empty space. The Earth pulled on the Moon. The Sun pulled on the Earth. A stone in your hand was pulled by the whole planet beneath you. But how exactly did that happen? What was the medium? What was doing the pulling? How did one mass reach across the void and affect another without anything visible in between? This troubled some people at the time, and Newton himself was not entirely comfortable with the idea of action at a distance. It worked mathematically, yes, but it felt unsettling. Forces, after all, are easiest to imagine when there is contact. A hand pushes a cart. A rope pulls a bucket. A gust of wind bends a branch. Even air, though invisible, gives signs of itself in motion. But gravity in Newton's picture needed no direct contact and no obvious medium. It simply acted. Across emptiness. Reliably, invisibly, and with no apparent delay in the original formulation. That was powerful, but also philosophically awkward. Still, the success of the theory was so overwhelming that most people were willing to live with the discomfort. Results have a calming effect on doubt. If your idea correctly predicts eclipses and planetary paths, people tend to forgive a little mystery at the centre. And Newtonian gravity kept earning that forgiveness over and over again. The picture it offered was appealing in its own right. Space was like a vast stage, fixed and unchanging. Time flowed evenly everywhere. The same for all observers, a kind of universal cosmic clock. Objects moved through this stable backdrop, and forces explained why their motions changed. Gravity was one of those forces, perhaps the grandest of them all. It was universal. It acted on everything with mass. It never switched off, and unlike the forces we encounter in daily life, it was always attractive. Gravity did not shove things apart. It drew them together. That gave the universe cohesion. It explained why matter gathered into planets and stars instead of dispersing politely into nothing. There was something deeply satisfying in that image of order, the universe as mechanism, the heavens as lawful, motion as calculable. Newton's achievement fit beautifully with an age that increasingly believed nature could be understood through reason and mathematics. He did not merely add a new law. He helped establish a whole way of thinking about the physical world, find the forces, write the rules, predict the motion. Again and again, the method worked. Even in ordinary life, Newton's view remains wonderfully useful. If you drop your keys, Newton tells you why they fall. If you throw a ball, Newton describes its arc. If engineers want to build a bridge, launch a satellite, or calculate the pull between bodies in many practical settings, Newton is still right there, calm and competent, quietly doing excellent work centuries after his death. This is worth emphasizing because when Einstein later revised our understanding of gravity, he did not make Newton foolish. He made him incomplete. That is a very different thing. Newton was not replaced because his theory failed in everyday life. He was surpassed because the universe turned out to be even stranger and more subtle than his already remarkable framework had revealed. But before we get to that strangeness, it is worth dwelling a little longer with what Newton actually gave us, because the invisible pull of the universe was not just a convenient rule, it was a profound act of simplification. The world is full of distracting detail. Apples fall in orchards, moons circle planets, tides rise and recede, comets appear from darkness and vanish again. It would be easy to treat each of these as a separate phenomenon requiring separate explanation. Newton refused that clutter. He saw pattern where others saw variety. He reduced the many to the few. That is one of the deepest scientific instincts, and when it succeeds, it changes everything. There is also a quiet psychological reason why Newton's picture still feels natural to many people. Forces are intuitive. We feel pushes and pulls all the time. The idea that the Earth pulls you downward has an immediate grip on the imagination. It matches daily experience. If you lift a suitcase, you feel resistance. If you set it down, it drops. It feels entirely sensible to describe this as a force between the suitcase and the Earth. Newton's gravity speaks the language of common sense, only refined and universalized. That is one reason Einstein's later picture feels harder at first. Curved spacetime is not part of ordinary intuition. Invisible attraction, oddly enough, is. And Newton's view carried another powerful implication. If gravity acts between all masses, then the universe is fundamentally interconnected. Not in a mystical sense, but in a precise physical one. Every object influences every other object to some degree. Your body attracts the chair attracts the floor, the Earth attracts the moon attracts the oceans. The sun holds the planets in their long paths, while each planet tugs back ever so slightly on the sun. Gravity makes isolation impossible. The universe becomes a web of mutual attraction, stronger here, weaker there, but everywhere present. That mutuality helped explain tides in a particularly beautiful way. The oceans do not rise and fall simply because the moon pulls on them in some crude, one-sided manner. The Earth and moon interact, and different parts of the Earth feel that interaction differently. Newton's gravity made sense of that. It explained why there are patterns to the tides, why they shift with the moon, and why celestial motion and seaside rhythms belong to the same physical order. Again, it joined the intimate and the immense. His theory also explained the shapes of planetary orbits with remarkable success. Planets do not move in perfect circles, despite the old philosophical affection for circular perfection. They follow more subtle paths. Newtonian gravity accounted for this. It allowed astronomers to understand planetary motions with a level of confidence that had previously been unreachable. The sky became less mysterious in one sense, though never less impressive. Predictability did not ruin wonder, it sharpened it. And yet that hidden discomfort never vanished entirely. The invisible pull remained just that, invisible. One mass acts on another at a distance, yes, but by what mechanism? Through what structure? Why should mass produce attraction at all? Newton's law told you how much attraction there would be, and that is no small thing. But it did not tell you why the universe was built in such a way that mass should attract mass. It described the rule without exposing the machinery behind it. This gap became more important as physics advanced. Other forces began to acquire richer descriptions. Electricity and magnetism, once mysterious in their own right, were eventually woven into field theories. They were no longer just pushes and pulls at a distance. They involved structures filling space. They had waves, propagation, and a deeper conceptual framework. Gravity, in the Newtonian sense, began to seem somewhat old-fashioned by comparison, not because it had stopped working, but because its underlying picture remained austere and a little too silent about the medium of influence. There were also small but persistent anomalies. Most motions in the solar system fit Newton's picture beautifully, but not every detail lined up perfectly. One of the most famous involved Mercury. The innermost planet moved in a way that was almost but not quite what Newtonian gravity predicted. The discrepancy was tiny, and for a long time people hoped it could be explained away by some unseen planet or unaccounted for matter. That was a sensible hope. Newton had earned the benefit of the doubt many times over. But the anomaly remained, a faint unease in an otherwise superb account. Meanwhile, light posed another subtle challenge. In Newton's universe, gravity acts on mass. But what exactly should happen to light? Newton himself had ideas about light that differed greatly from later understanding, and the full relationship between gravity and light would have to wait. Still, the question lingered. If gravity is a universal feature of nature, should it affect light as well? And if so, how? The Newtonian framework had no especially natural way to make that connection central. Then there was the matter of time itself. In Newton's world, time is absolute. It flows at the same rate everywhere for everyone. Gravity influences motion through space, but time remains untouched, a steady background parameter. That assumption feels harmless at first because daily life offers no obvious reason to doubt it. Your watch ticks. My watch ticks. Tea cools. Bread burns if neglected. Everything seems to proceed in a shared temporal order. Yet once the foundations of relativity began to emerge, that comfort would not survive. Time would become part of the gravitational story, and Newton's serene universal clock would begin to wobble. Still, none of that should obscure how extraordinary his achievement was. Newton gave humanity a universe that could be reasoned with. He did not banish mystery, but he disciplined it. He showed that the motions of the heavens were not divine habits beyond comprehension, but lawful processes open to analysis. He gave gravity mathematical form. He made prediction possible on a grand scale, and perhaps most impressively, he made a vast and varied cosmos feel like one connected physical system. There is something almost heroic in the simplicity of that invisible pull. No warping spacetime yet, no geodesics, no clocks running differently near stars, just masses attracting masses across the quiet of space. If you were to stand in Newton's world, it would feel solid and comprehensible. Gravity is a force. The Earth pulls you down. The sun pulls the planets inward. The moon is held in orbit by attraction. Everything has its place in a grand mechanical order. But as satisfying as that picture was, the universe was already preparing its objection. The objection would come not as a total rejection, but as a deep correction. It would say, in effect, that the invisible pull is not quite the right way to think about gravity after all. Useful, yes. Brilliant, yes. But not fundamental. What looks like attraction may actually be the consequence of geometry. What seems like force may arise from the shape of space-time itself. And once that possibility enters the story, Newton's universe, so stable and orderly, begins to tilt towards something even more surprising. If Newton gave gravity its first great unifying story, Einstein came along and changed the meaning of the story itself. He did not simply adjust a few details, tidy up a corner, or add some helpful footnotes for the mathematically enthusiastic. He changed the foundation. He looked at gravity, that familiar and apparently reliable pull between masses, and decided that what everyone had been calling a force might not be a force in the ordinary sense at all. That is a remarkable thing to do to one of the most successful ideas in the history of science. It is rather like inheriting a beautifully crafted clock, admiring how accurately it keeps time, and then announcing that it is not really a clock in the way people think, but something far stranger that only happens to tell the time as a side effect. To appreciate how bold this was, it helps to remember just how well Newtonian gravity worked. Planets moved as Newton said they should. Objects fell as Newton said they should. Tides, trajectories, celestial paths, all of them could be handled with tremendous success. So Einstein was not solving a problem in the ordinary everyday sense. Apples were not refusing to fall. The moon was not wandering off in protest. The old picture still performed beautifully in most situations. the problem was subtler. The closer physicists looked at the structure of nature, the more the old language of forces acting across space began to feel incomplete. It worked, but it did not quite satisfy. It described what happened, but not in the deepest possible way. Einstein had already disrupted physics once before he turned fully to gravity. In the early years of the 20th century, he had shown that space and time were not the separate fixed backgrounds many people had assumed. They were linked. Measurements of distance and duration depended on the motion of the observer. The speed of light stayed the same for all observers, and once that fact was taken seriously, many older assumptions had to go. Time could stretch. Length could contract. Simultaneity, that wonderfully confident idea that two events either happen at the same time or they do not, turned out to be more complicated than it seemed. What felt absolute in daily life was not absolute in the structure of the universe. That alone would have been enough for most scientific careers and probably several very smug dinner conversations. But gravity remained unfinished business. Newton treated gravity as a force acting between masses. Einstein had already shown that space and time were not rigid containers, so the question became difficult to ignore. If space and time themselves are more flexible than we thought, then perhaps gravity is not something taking place within space-time in the old ordinary way. Perhaps gravity has something to do with the structure of space-time itself. The crucial step toward that new view came from one of Einstein's simplest and most famous ideas, the equivalence principle. It sounds formal, but the basic intuition is surprisingly direct. Einstein realized that there is a deep connection between gravity and acceleration. More than that, in small enough regions, the two can be physically indistinguishable. Imagine you're inside a sealed lift. No windows, no clues, just you and the interior of the cabin. If the lift is standing on Earth, you feel your weight in the usual way. Your feet press against the floor. If you drop a small object, it falls downward. All perfectly ordinary. Now imagine instead that the lift is far from any star or planet, deep in empty space, but it is being pulled upward by a rocket with steady acceleration. You would feel pressed to the floor in much the same way. If you let go of an object, it would appear to fall toward the floor. From inside the lift, in a sufficiently small region, those two situations would look the same. That is already a little unsettling. It suggests that what we usually call gravity and what we call acceleration might not be fundamentally different kinds of things. Then Einstein asked the opposite question. What if the lift on Earth is suddenly allowed to fall freely? For a brief time, everything inside falls together. You float relative to the cabin. Loose objects drift. The familiar feeling of weight disappears. In that local environment, gravity seems to vanish. Of course, it has not truly vanished in the wider sense. The whole lift is falling under gravity. But inside, the effect is transformed. What remains is a kind of local weightlessness. That was the key insight. A freely falling frame is, locally, like an inertial frame without gravity. And a uniformly accelerating frame can mimic the effects of gravity. This was not just a clever observation about lifts. It pointed toward a much deeper truth. If gravity can be transformed away locally by going into free fall, then perhaps gravity is not an ordinary force in the old Newtonian sense. A real force, such as a push from a wall or a pull from a rope, does not disappear simply because you choose a different frame of reference. But gravity, at least locally, can. This is the point where Einstein began to move beyond Newton in a way that changes everything. If free fall feels force-free, then maybe falling is not what needs explaining as a forced motion. Maybe it is the natural motion. Maybe what needs explaining is why standing still on the ground feels like something is happening to you. And the answer, as we have already begun to see, is that something is. The ground pushes on you. It prevents you from following the path you would naturally take. That path, in Einstein's view, is not determined by an invisible pull acting across a static space. It is determined by the geometry of space-time. That phrase can sound larger and more ceremonial than it really needs to. Geometry simply means shape and structure. In school, geometry concerns circles, triangles, angles, surfaces, and distances. Einstein took that idea and applied it to the universe itself. Space-time has shape. It is not flat and passive everywhere. Mass and energy affect it. They alter its structure. And once that structure is altered, the straightest available paths are no longer what they would be in an uncurved world. It helps to be careful here because this is often the moment where explanations have become a little too fond of rubber sheets, bowling balls, and marbles rolling around on stretched fabric. Those images can be useful at first, but they also cause trouble because they smuggle ordinary gravity back into the explanation. A marble rolling on a sheet falls inward because gravity is already pulling it downward through the sheet. So while the analogy hints at curvature, it is not the whole story and can leave people more confused than comforted. A better way to approach it is to think about what it means for motion to be straight. In ordinary flat space, if nothing acts on an object, it keeps moving in a straight line. That is a familiar principle. But in curved geometry, straight lines are not always what common sense expects. On the surface of a globe, for example, the most direct route between 2 points is not the sort of straight line you would draw on flat paper. The geometry changes what counts as the straightest possible path. Einstein's great move was to say that gravity changes what counts as straight motion through space-time. So objects do not fall because a mysterious force reaches out and drags them inward in the old ordinary picture. They fall because in the curved space-time around a massive body, the natural paths available to them lead the way we describe as downward. A planet orbiting the Sun is not being yanked around a corner by an invisible tether. It is following the straightest possible path available in the curved space-time created by the Sun's mass and energy. The same idea applies to light, which becomes especially important because light has no mass in the usual sense, and yet it too follows the geometry. This was an extraordinary shift in understanding. Newton had asked what force acts on a body, and how does that force change its motion? Einstein asked what kind of space-time does the body move through, and what path is natural in that space-time. One picture is dynamic objects on a fixed stage. The other is dynamic objects on a stage whose very shape participates in the drama. Gravity is no longer one actor among many. It is part of the structure in which the acting happens. Developing this into a full theory took Einstein years of work and a great deal of mathematical effort. The finished theory, general relativity, arrived in the middle of the First World War, which is a rather inconvenient time to produce one of the greatest intellectual achievements in human history. Though the universe does not generally pause for administrative convenience, general relativity says, in essence, that mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. That is the heart of it. No invisible force reaching across empty space in the old way. No universal stage untouched by the players. Instead, matter, energy, space and time are woven into one interacting system. One of the reasons this feels difficult at first is that it asks us to stop treating time as an innocent bystander. In Newton's world, time flows uniformly and independently. Gravity acts in space, but time itself stays steady. In Einstein's theory, time becomes part of the geometry that mass influences. Near a massive object, time runs differently. That is not metaphorical, and not a small decorative detail added after the main argument. It is central. Gravity is not only about where things go, it is also about how rapidly clocks tick. This is one of the most startling consequences of Einstein's rewrite, because it pushes gravity beyond motion into the domain of duration itself. Two clocks at different heights in a gravitational field will not agree forever if they are precise enough. The one deeper in the gravitational field runs more slowly. Again, this is not because the clock is broken or sulking or in need of better batteries. It is because time itself is part of what gravity affects. Once you accept that, many things that seemed unrelated become aspects of the same geometry. Falling bodies, orbiting planets, bent light, shifting time, all of them belong together. Now, one perfectly sensible reaction at this stage is to say that this is all very elegant, but perhaps a little too elegant, which is often the polite way of asking whether nature truly behaves this way, or whether physicists have simply become too attached to theories that sound impressive in quiet rooms. Einstein needed evidence, and eventually the evidence came. One of the earliest great successes involved the orbit of Mercury. Newton's theory predicted Mercury's motion almost perfectly, but there was a tiny leftover discrepancy that refused to go away. General relativity accounted for it naturally, not by patching the theory with a desperate extra ingredient, but by describing gravity differently from the ground up. That mattered because it showed Einstein's theory was not merely philosophically attractive, it was quantitatively better where the old theory strained. Then came another powerful test. If gravity is geometry, then light should follow curved paths near massive bodies because it follows space-time too. During a solar eclipse, stars appearing near the edge of the sun should look slightly shifted because their light bends as it passes through the curved space-time around the sun. Observation supported this. The effect was small, but it was there. Light itself responded to gravity not as a conventional force on a little massive particle, but as a consequence of geometry. That result helped make Einstein world famous, though being world famous for space-time curvature is probably not as restful as it sounds. More importantly, it confirmed that gravity was broader than Newton had imagined. It affected not just masses, but the structure of paths themselves, including the paths of light. And the theory kept proving itself in ways that later generations could hardly ignore. Time dilation in gravitational fields turned out to be measurable. Satellite systems that depend on extremely accurate timing must account for relativistic effects. If they did not, navigation would drift disastrously. Gravitational waves, tiny ripples in space-time produced by enormous accelerating masses, were eventually detected directly. Black holes, once a peculiar implication of the equations, became observed astrophysical objects with growing evidence behind them. Again and again, Einstein's rewrite showed that it was not merely an intellectual rebranding of gravity. It was a deeper description of reality. Still, what makes the theory so gripping is not only the list of predictions it gets right, it is the way it changes the meaning of ordinary experience. When you stand on the ground, you are not simply being held in place against a downward pull. You are being kept off your natural path through space-time. The ground presses upward. Your weight is the result of that support. A person in free fall feels no such support and therefore feels no weight, even though gravity in the broader geometric sense is doing exactly what it always does. That is a different way of thinking about the world from the one most of us inherit in childhood. It also changes the meaning of orbit. A satellite is not constantly firing invisible little corrections to avoid falling. It is in free fall already. It is following a geodesic, the natural path laid out by the curved space-time around Earth. The fact that the path closes around the planet rather than diving into it or shooting away is a consequence of the geometry and the satellite's motion through it. The same is true of planets around stars. They are not held in place by something like a cosmic leash. They are moving freely in a curved structure. Even the phrase warping space-time, though common and not incorrect, can accidentally make it sound as though matter is doing something theatrical to an otherwise neutral substance. What Einstein really gave us was a unified way to understand gravity as geometry, not a pulling force layered onto the universe from the outside, but a property of the universe's structure. Mass and energy do not sit in space and time as if they were furniture in a room. They participate in shaping the room itself. This is why Einstein's great rewrite feels so profound. He did not merely improve a theory of falling objects. He altered the relation between matter and the world it inhabits. He removed gravity from the category of ordinary forces and placed it into the architecture of reality. That is a major reclassification. It is the difference between thinking that traffic is caused by bad drivers and realizing the road network itself is designed in a way that channels motion into certain patterns. One explanation focuses on pushes and pulls within a fixed environment. The other says the environment is part of the explanation. Of course, daily life is not much inconvenienced by whether one prefers Newton's force or Einstein's geometry. A dropped mug remains a matter of some concern either way. One should still hold onto railings and avoid testing gravity from balconies. But once you want to know what gravity really is, the old story begins to feel too flat. Einstein did not deny that objects accelerate toward massive bodies. He explained why that happens without relying on the simple picture of an invisible pull. He showed that the universe is more subtle than that. What is especially striking is how this new view makes free fall the most natural state available under gravity. Standing still becomes the unusual case. That can take a while to get used to because it feels backwards. But it is one of the clearest signs that Einstein has genuinely changed the framework. In Newton's world, gravity acts on you and makes you fall. In Einstein's world, the geometry guides your free motion and makes falling natural. The force you actually feel comes from being prevented from that motion by the ground, the chair, the bed, the floor of a lift, or anything else solid enough to insist on an alternative arrangement. Once that has settled in, a new question comes into view. If Einstein is right that free fall is the natural path, and if the feeling of weight comes from being pushed away from that path, then what exactly does free fall feel like from the inside, and why does an object in free motion through curved space-time experience no force at all? There is something deeply misleading about the way falling looks from the outside. From the ground, a dropped object appears to be doing something dramatic. One moment it is supported, then it is released, and at once it accelerates downward. It picks up speed. It covers more distance each moment. If it is fragile, everyone in the room suddenly becomes much more attentive. The whole event looks forceful. It looks as though something has begun acting on the object in a very direct and rather urgent way. So it feels natural to say that the falling object is under the force of gravity, and that this force is what the object ought to feel. But this is exactly where Einstein asks us to slow down and separate appearance from experience. Because from the point of view of the falling object itself, something very different is happening. In free fall, there is no sensation of force in the ordinary bodily sense, no pressure from below, no strain in the limbs caused by support, no upward push from a floor, a seat, a scale, or a mattress. The object is not being held up, not being resisted, not being compressed by contact with a surface that refuses to let it continue. It is simply moving along the path available to it. That is why free fall feels like no force at all. This can seem almost perverse the first time you really sit with it. We are so used to describing gravity as the force that makes things fall that the claim sounds backwards. Surely, if anything, falling should feel like the clearest possible example of gravity at work. And yet what Einstein realized is that the sensation we usually associate with gravity is not the sensation of falling. It is the sensation of being prevented from falling. Weight is what a supporting surface feels like. Free fall removes that support, and when support vanishes, so does the sensation of weight. A useful place to begin is with something familiar and slightly unpleasant, because unpleasant experiences often have the courtesy to be physically instructive. Think again about a lift that begins descending more quickly than expected. There is that little dip in your stomach, that brief feeling of lightness. Or think of the moment a roller coaster tips over the crest and begins its drop. Or the instant you miss a step on the stairs and your body realizes before your mind does that the floor is not where it had scheduled it to be. In each case, what changes is not the existence of gravity. What changes is the support force. The floor beneath you is no longer pushing upward with the same strength, and your body immediately notices. Now imagine taking that reduction of support all the way, not just a brief softening, but a complete absence of support. No floor pressing on your feet, no chair supporting your back, no bed under your shoulders, no scale pushing upward so that it can report your private business with numerical certainty. If you and everything around you were falling together, there would be no contact force among you caused by support. Locally, you would float. That is what free fall is like. It is not the experience of being yanked downward by some invisible hand. It is the experience of having the usual interruptions removed. This is why astronauts feel weightless in orbit. It is worth returning to them because they remain one of the clearest examples, and also because the phrase zero gravity has misled generations of people into imagining that astronauts float because gravity has somehow gone on holiday. But gravity is not absent where they are. If it were, they would not stay in orbit around Earth. They would drift off in whatever direction their motion happened to take them, which would make for a very different space program and a noticeably worse commute home. The reason astronauts float is that they and their spacecraft are in free fall together. They are continually falling around Earth. Nothing inside the spacecraft is supporting them in the way the ground supports you right now. Since the floor is not pressing upward on them, they do not feel weight. Gravity is present, but support is absent. And without support, the ordinary bodily experience of force disappears. This is one of the most important distinctions in all of relativity. Gravity in Einstein's picture is not like being shoved by a wall or pulled by a rope. Those are contact forces, or at least forces with effects that cannot be transformed away by simply choosing a freely falling frame. If a wall presses on your back, you feel it. If a rope tugs your arm, you feel it. But if you are in free fall under gravity alone, there is nothing in your local immediate environment that must feel unusual. You do not sense gravity as a force acting on you, in the way you sense support or pressure. Instead, you move naturally through space-time, following what is called a geodesic. The closest thing curved space-time has to a straight path. That word geodesic can sound a little formal, but the idea is straightforward. In ordinary flat space, the natural unforced path is a straight line at constant speed. In curved space-time, the natural unforced path can look very different to an outside observer. Near Earth, for example, the geodesic path of an unsupported object leads inward in a way we describe as falling. The important point is that the object is not feeling a force in the usual sense while doing so. It is simply following the path available. Free fall is what unforced motion looks like in a gravitational field understood geometrically. This is one reason Einstein considered freely falling frames so fundamental. If you're enclosed in a small falling box and cannot see outside, local experiments will make it seem as though gravity has vanished. Objects released beside you will float relative to you. If you toss a ball gently, it will drift in a straight path relative to your local frame. For that brief local region, physics looks like ordinary inertial motion without gravity. That is not a coincidence or a trick of language. It reflects the deep structure of general relativity. Gravity can be transformed away locally by moving into free fall because free fall is the natural motion dictated by space-time geometry. Of course, one must be careful with the word locally. If the box is large enough or the fall lasts long enough, differences in the gravitational field from one place to another will reveal themselves. These are tidal effects. One part of the box may be pulled slightly differently from another. Two freely falling objects released side by side may drift closer together or farther apart depending on how the space-time curvature varies across the region. So gravity is not globally gone in free fall. But in a sufficiently small region, its force-like character disappears. That is why Einstein could say something so radical. A person in free fall feels no gravitational force. There are real-world examples, modest but persuasive, that help make this more concrete. Consider the short periods of weightlessness experienced in aircraft performing parabolic flights. These are sometimes called vomit-comet flights, which is a very honest name, and perhaps a small warning about the limits of scientific romance. During portions of the flight, the aircraft and everything inside it follow a freefall trajectory. Passengers float, objects hover. Drinks, if unwisely handled, become democratic in their distribution. What the passengers feel in those moments is not some powerful downward drag, but the absence of support. The floor is not holding them up in the ordinary way, so their bodies no longer register weight. The same thing happens in much simpler circumstances, though usually too briefly for anyone to enjoy it. Jump from a chair, hop off a low wall, or toss an object upward and watch it come down. During the airborne phase, the object is in free fall. If it had a nervous system and a talent for reflection, it would not report being under pressure. It would report nothing unusual until the ground intervened. That is always the key moment. The force you feel is not during the free motion, but during the interruption of it. In fact, impacts tell the story very clearly. When a falling object hits the ground, that is when stresses become large. That is when things bend, break, compress, or complain. The floor exerts an upward force that changes the object's motion abruptly. That force is felt because it is a true local interaction. During the fall, before the impact, there is acceleration relative to the ground, yes, but no internal support force of the sort we associate with weight. Once the ground stops the fall, the object is no longer following its geodesic. The support force returns with enthusiasm, and the body or object experiences it directly. This is why standing still on Earth is, in a deep sense, stranger than falling. When you stand on the ground, the surface beneath you prevents you from taking the natural freefall path through space-time. It pushes upward on your feet. Your skeleton carries that load. Your muscles make adjustments. Your tissues experience slight compression. All of this is so familiar that it feels unremarkable, but physically, it is a continuous state of supported deviation. You're not moving as freely as a falling object. The falling object is. That reversal takes time to become intuitive, because our language evolved for daily survival, not for geometric interpretations of gravity. If someone says be careful, you're about to fall, they are not making a mistake. Falling remains hazardous, and no one should respond by announcing that one is merely attempting to follow a geodesic in a more authentic manner. That would be both impractical and deeply annoying. But when the question is not practical safety but physical understanding, the distinction matters. Freefall is not the presence of a felt force, it is the absence of support, and that is why it feels like no force at all. Einstein's equivalence principle sharpens this further. If being in a small, freely falling frame is locally equivalent to being far from gravity, then gravity does not behave like an ordinary force. Instead, it reflects the fact that different freely moving frames are oriented differently in curved space-time. What you interpret as gravitational acceleration from the outside is, from the inside, simply inertial motion along a curved background. The body experiences no local shove. It is the geometry that changes what counts as straight. Another way to think about it is through comparison with other forces. Suppose you're inside a car that suddenly accelerates forward. You feel pressed back into the seat. That pressure is real and unmistakable. Or suppose the car takes a sharp turn. You feel yourself pushed sideways against the door, or at least you do until the seatbelt offers its very firm opinion. Those sensations come from contact forces. The car is changing your motion away from what it would otherwise be. Your body resists, and support surfaces supply the necessary force. By contrast, if the car were somehow allowed to drive off a cliff and fall freely, for a brief interval before the rest of the experience became less educational and more regrettable, you would feel lighter, not heavier. The sensation of force would lessen because the seat would no longer need to support your weight in the usual way. Again, the distinction is between support and free motion. This is why scales are such useful little philosophers of gravity, despite their unfortunate bedside manner. A scale does not measure gravity directly. It measures the support force between you and itself. In free fall, that reading drops to 0. Not because Earth's gravity has ceased, but because there is no longer any upward push. The scale is falling with you. It has nothing to press against. In that condition, the bodily experience of weight vanishes as well. Your weight, in the operational sense a scale can detect, is gone. One of the most elegant consequences of all this is that gravity becomes less a matter of feeling pulled and more a matter of noticing when you're prevented from moving freely. A person sitting quietly in a chair is continuously experiencing support. A person floating in orbit is not. The chair-sitter may look calm and stationary, while the astronaut may appear to be in a strange dramatic environment. Yet in one deep physical sense, the astronaut is closer to the natural gravitational motion. The chair-sitter is the one being pushed away from it. There is also something important here about bodily perception. Human beings do not possess a special organ that directly senses space-time curvature. We do not have a little internal meter that lights up and says gravity field detected. What we sense are pressures, accelerations, strains and contact forces acting on our bodies. When you feel heavy, you are feeling compression and support. When you feel weightless, those support patterns have faded. In free fall, your organs, muscles and bones are no longer being held against supporting surfaces in the same way. That is why the experience is so distinctive. The body is exquisitely tuned to support and acceleration, not to gravity as a separate abstract entity. This explains why weightlessness can feel so disorienting at first. The body is accustomed to using gravity indirectly through support. Your sense of up and down, your balance, your posture, all depend partly on the constant interaction between body and surfaces. Remove that interaction, and the nervous system has to improvise. Astronauts often need time to adjust, not because gravity itself has ceased in some metaphysical sense, but because the normal signals of support and pressure have changed dramatically. The body is no longer receiving the same steady reminders of which way the floor insists on being. Even the language of falling reveals how much common sense resists the deeper picture. We say an object falls under gravity as if that were a complete description, and for many purposes it is enough. But the more exact statement would be that an unsupported object near Earth follows a geodesic through curved space-time, while a supported object is pushed away from that geodesic by contact forces. That is not the sort of sentence one casually inserts into a family conversation over biscuits, but it is closer to the truth. And once you understand it, many puzzling things become less puzzling. For instance, why does an orbiting astronaut feel weightless while still being under strong gravity? Because weight is support, not gravitational presence. Why does a person in a freely falling lift float relative to the lift? Because both are following nearly the same geodesic. Why does standing on Earth feel like a force while floating in orbit does not? Because the ground presses on you and the spacecraft cabin in free fall does not have to. All of these are versions of the same insight. There is also a subtle but important humility in this picture. It reminds us that what feels obvious is not always what is fundamental. Everyday experience tells us that standing still is normal and falling is a special event caused by gravity. Relativity tells us that free fall is the simpler state, and standing still on a planetary surface is the supported exception. That is not merely a technical correction. It is a rearrangement of what counts as natural motion in the universe. And once that rearrangement is taken seriously, the world becomes slightly stranger in a very productive way. Floors become active participants rather than passive backgrounds. Chairs become little devices for denying geodesics. Elevators become thought experiments waiting to happen. Astronauts become examples not of escaping gravity, but of surrendering to it more completely than most of us ever do. And the feeling of weight, that ordinary, familiar heaviness we have carried without much question all our lives, starts to reveal itself as the signature not of gravity alone, but of matter, interrupting free motion. So when an object falls freely and feels no force, that is not a paradox or a trick. It is the clearest sign that Einstein's rewrite of gravity has begun to take hold. The falling object is not being tormented by an invisible pull in the way common sense first imagines. It is moving naturally. The force enters when something stops that motion. The force enters when the ground arrives, when the chair supports, when the floor resists, when the bed catches you, when the scale pushes back. Free fall removes those interruptions and with them the feeling of weight. And once that is clear, the next step becomes impossible to ignore, because if falling is the natural path and weight comes from being prevented from taking it, then standing still on Earth is not nearly as quiet or ordinary as it first appears. Once you begin to accept that free fall is the natural motion and that weight comes from support rather than from gravity acting like an ordinary pull, an even stranger idea comes into view. Standing still on Earth is not the calm, neutral condition it appears to be. In a deep physical sense, it is a managed interruption. It is a state of being continuously pushed away from the path you would otherwise take. Falling, which looks dramatic and disruptive, turns out to be the simpler case. Standing still, which feels ordinary and uneventful, is the one that requires explanation. That is not the way we usually talk, of course, and for good reason. In everyday life, standing still feels like the default. You are in the kitchen. You are waiting for the kettle. You're standing in a queue that seems to have been designed by someone with a deep commitment to testing human patience. Nothing appears to be happening. Your position is stable. Your body is at rest relative to the floor. The whole scene feels so unremarkable that it hardly seems like the sort of thing that should belong in a discussion about the deep structure of the universe. Falling, by contrast, looks like a special event. It starts suddenly. It produces visible acceleration. It often ends in a regrettable noise. So common sense places the drama in the fall and the simplicity in the standing. Einstein asks us to reverse that. The reason is simple once you let the earlier idea settle properly. A freely falling object follows its natural path through curved space-time. Nothing local has to push it into doing that. It just goes. A person standing on the ground is not following that path. The ground beneath them prevents it. The surface pushes upward on their feet, and through their feet on the rest of their body. That upward push is not optional. It is not a decorative extra. It is what keeps them from falling. So standing still on Earth is not the absence of force. It is the presence of a continuous support force. This is why the phrase standing still is stranger than falling is not merely a rhetorical flourish. It is a precise statement about what requires local physical intervention. Falling happens when the intervention is removed. Standing requires the intervention to continue every second. It helps to look at what your body is actually doing when you are motionless. If you're standing upright, the ground presses upward on the soles of your feet. Your feet transmit that force to your ankles to your legs to your hips and spine, and so on through the whole structure of your body. Muscles make tiny adjustments constantly to maintain balance. Bones carry load. Tissues experience pressure. None of this feels especially dramatic because it is familiar, but it is active. Your body is not passively existing in place. It is responding to support. The floor is not quietly minding its own business. It is continuously refusing to let you follow your freefall path. That is why standing for a long time becomes tiring. If standing still were truly the most neutral state, it would be odd for the body to complain about it so steadily. But the body does complain. Feet ache. Legs grow restless. Backs begin offering commentary. The reason is not simply that humans are poorly engineered for patience, though one could make a case for that too. It is that standing means supporting and balancing a body against the persistent upward force of the ground, while gravity shapes the natural path that the ground is blocking. All of that has mechanical consequences. You can notice a milder version of the same thing when you lie down. Lying in bed usually feels restful, and in many ways it is, but it is not the same as being force-free. The support is merely distributed differently. Instead of the entire load passing through your feet, it is spread across your back, hips, shoulders, and legs. Pressure points shift. The mattress pushes upward across a wider area. The body relaxes because the support is less concentrated and balancing is easier, not because support has disappeared. If the mattress vanished, rest would become brief and much more educational. A chair does something similar. When you sit, the chair takes over much of the work your legs were doing, and your body often responds with gratitude. But again, the chair is providing support. It is pushing upward on you. The fact that it does so politely does not change the physics. The sensation of being seated is the sensation of a surface preventing free fall in a particular arrangement. The reason it feels so ordinary is not that no force is present, but that the force is steady and familiar. One very useful way to sharpen this idea is to compare standing on Earth with accelerating in empty space. Imagine a spaceship far from stars and planets, with no meaningful gravitational field nearby. If the ship fires its engines and accelerates steadily upward, the floor of the ship will press against the feet of the passengers. They will feel weight. Loose objects released in the cabin will appear to fall toward the floor. A cup set down incautiously will not float away. To the people inside, it may feel remarkably like being on Earth. Their bodies register pressure, support, and heaviness. Their bones and muscles behave much as they do on the ground. That comparison is not just a science fiction curiosity. It tells us something deep. The bodily experience of weight does not depend on knowing whether one is on a planet or in an accelerating rocket. It depends on being pushed by a supporting surface. If a rocket in empty space can produce the same local experience as standing on Earth, then the experience of weight cannot by itself be the direct sensation of gravity as an invisible pull. It is the sensation of proper acceleration, the acceleration you actually feel because something is pushing on you. That term proper acceleration may sound a bit formal, but it captures an important distinction. There is the kind of acceleration that shows up when your path changes relative to something else, and then there is the kind of acceleration your body locally experiences as pressure or strain. In Einstein's picture, a person standing on Earth experiences proper acceleration upward because the ground is pushing on them, even though from the everyday point of view they are not moving at all. A freely falling person accelerates downward relative to the ground, yes, but experiences no proper acceleration because nothing is pushing on them locally. That is why free fall feels weightless, and standing still does not. This leads to one of the loveliest little physical ironies in the modern world. The sensors in your phone that help detect orientation and motion do not think of your resting body the way common sense does. An accelerometer measures proper acceleration, the kind associated with actual support forces. So when your phone lies still on a table, from the point of view of that sensor, it is not experiencing zero. It is experiencing an upward acceleration because the table is pushing on it. If the phone were dropped, the sensor reading would change towards zero during the fall because the support vanishes. So your phone, in its own unromantic way, agrees with Einstein. Resting on a table is not the force-free state. Falling is closer. There is something wonderfully rude about that. You set your phone down and think nothing is happening. The phone, if it had opinions, might say quite the opposite. It is being supported. It is being prevented from following its natural path. It is under stress, however mild. Drop it, and for a brief instant before other concerns take over, it becomes more nearly force-free than it was on the table. This is not the sort of fact that improves anyone's relationship with dropping phones, but it is a very tidy illustration of the principle. Once you see that, many ordinary situations start to look different. An apple sitting on a branch is not simply at rest in some neutral sense. The branch exerts a force on the stem and through it on the apple. The apple is being held away from its free-fall path. When the stem gives way, the apple is not suddenly forced into an unnatural motion. It is released into a more natural one. A book resting on a shelf is under support. Remove the shelf, and the book follows its path through curved spacetime until something else interrupts it. A lamp on a table, a mug on a desk, a cat on a windowsill pretending it has never broken anything in its life, all of them are being held off their geodesics by the surfaces beneath them. This is why surfaces matter so much in the relativistic picture of gravity. They are not just convenient places where objects happen to stop. They are the agents of deviation. They are what push objects away from free motion. Every floor is engaged in a continuous act of refusal. Every chair is a small anti-geodesic device. Every mattress is a carefully cushioned rebellion against free fall. That may sound grander than furniture usually deserves, but physically it is accurate. It also helps explain why the human body experiences gravity the way it does. If you stand upright, the support forces are not distributed evenly. The feet feel the direct pressure from the ground. The legs and spine carry the load upward. Blood and other fluids settle differently than they do when you lie down. This is one reason prolonged standing feels different from floating, even though both can involve relative stillness with respect to the environment. On the ground, your body is under continuous support and compression. In free fall, those patterns largely disappear. Astronauts in orbit often report that the body feels strange at first, partly because the usual signals of support are gone. Fluids redistribute. Balance cues change. The body is no longer being organized by the steady upward push of the ground. You can see the opposite effect in high acceleration environments. Pilots in tight turns or riders on fast amusement rides feel heavier because support forces increase. Their seats push harder. Their bodies are forced away from the paths they would otherwise follow. This is not Earth somehow briefly becoming more massive in a mood. It is support intensifying. The body interprets that as greater weight because weight is precisely that kind of support force. There is another way in which standing still is stranger than falling, and it has to do with reference frames. In Newton's picture, space and time are fixed and absolute, so an object at rest on Earth is simply at rest unless acted on. In Einstein's picture, the deeper question is whether the object is following a geodesic, a natural path through space-time. A person standing on Earth is not. Their world line, their path through space-time, is being bent away from the geodesic they would take in free fall. The bending is not because gravity is pulling them in the old ordinary sense. It is because the surface beneath them imposes a different motion. That means the standing person is, in a real local sense, accelerated. Not moving upward through space like a rocket taking off, but experiencing the same kind of bodily acceleration a rocket passenger would feel if the rocket were steadily pushing upward in deep space. That is a remarkable claim. It means that the quiet stillness of standing on the ground is not inertial. It is maintained. It is supported. It is locally an accelerated state. By contrast, the person floating freely in orbit or falling in a vacuum chamber is inertial in the relativistic sense. They may be moving rapidly relative to Earth. They may be covering enormous distances. They may look anything but still from the outside. But locally they feel no force because they are following the natural geometry of space-time. So the everyday categories of still and moving become less important than the deeper distinction between supported and free. This is one of the places where relativity can feel almost impolite toward common sense. We are used to thinking that motion is the thing that must be caused, and rest is what happens when causes stop. Einstein says, not always. Free motion, even if it looks like falling or orbiting, is often the simpler case. Being held still on a planetary surface requires a real local force. Once that is absorbed, the old language of gravity as a pull begins to feel too coarse. It gets the rough direction right, but it misses the more interesting truth. There is also a useful lesson here about what bodies can and cannot sense directly. We do not feel gravity as geometry. We feel support, compression, tension, and acceleration. If you're blindfolded inside a sealed room, you can tell whether the floor is pressing on your feet. You can tell whether you feel heavy or light. But without looking outside, you may not be able to tell whether that comes from standing on Earth or from accelerating in a rocket. That is because your body is reading local forces, not the grand external picture. The body knows support. It does not know on its own whether the support is resisting gravity or being produced by engines. This was part of what made Einstein's line of thinking so powerful. He trusted the local physical equivalence of those situations enough to rebuild gravity around it. If standing on Earth and accelerating in a rocket feel the same locally, then perhaps gravity is not a conventional force after all. Perhaps what matters is the geometry of space-time, and whether you are following its natural paths. The standing person and the rocket passenger are both being pushed away from those paths by flaws beneath them. The freely falling person is not. Even a simple dropped object reveals the contrast. A ball resting in your hand is supported. Your hand must provide an upward force. The moment you release it, that force vanishes. For a while, until air resistance and then the ground complicate the story, the ball moves freely. It is not under local mechanical stress from support. If the ball could think, its most natural state would be that airborne interval, not the resting state in your palm or on the floor. The resting states are the ones that require an external structure to hold it off its path. This has consequences for how we talk about what gravity does. In ordinary speech, we say gravity makes things fall. In the deeper relativistic sense, gravity defines the structure in which free paths curve the way they do. Things fall because that is what straightest possible motion through curved space-time looks like near Earth. What prevents falling is not the absence of gravity but the presence of matter pushing back. So when you stand still, you're not simply resting inside gravity. You're resisting its geometric guidance by means of the surface under you. That is why standing still is not really still in the deepest sense. Your spatial position relative to the Earth may not change, but your path through space-time is being forced away from what it would otherwise be. Every second the ground continues its upward push, and every second your body continues to register that support as weight. The apparent calm of standing hides a continuous physical negotiation. There is something almost funny about how untheatrical this is. No sparks, no cosmic hum, no sense that space-time is being consulted in the hallway. Just feet on floorboards, a person waiting for a bus, a cat occupying a chair it did not pay for, a mug on a table, all of them quietly participating in one of the strangest truths in physics. The supported objects are the locally accelerated ones. The freely falling objects are the locally unforced ones. The world goes on looking ordinary while the interpretation beneath it changes completely. And once that shift really settles, another piece of the puzzle begins to ask for attention. If standing still on a planet means being pushed away from your natural path, then what exactly is it about mass and energy that shapes those natural paths in the first place? In other words, if gravity is not a downward pull, but a feature of space-time itself, then we need to look more directly at how mass bends not just space, but time as well. At this point, the idea that gravity is not really a conventional pulling force begins to feel less like a clever twist, and more like the start of a different way of seeing the world. But that shift only becomes fully convincing when we look more closely at what mass is actually doing. If falling is natural motion in curved space-time, and if standing still means being pushed away from that natural path, then the next question is very hard to avoid. What exactly is being curved, and how does that curvature involve not just space, but time as well? The answer is one of Einstein's greatest insights, and also one of the hardest to picture with ordinary intuition. Mass does not simply sit inside space-time as though space-time were a passive container. Mass and energy change the structure of space-time itself. They alter the geometry. They change what counts as the straightest available path. And because space-time includes time as well as space, the effect is never just about where things move. It is also about how quickly time passes along different paths. That last part is easy to say and surprisingly difficult to internalize, because most of us spend our lives treating space and time as separate matters. Space is where things are. Time is when things happen. You walk across a room, and that is space. You wait for the kettle to boil, and that is time. They feel different. They behave differently in everyday thought. One is something you cross. The other is something you endure, especially if the kettle has lost all sense of urgency. But relativity tells us that this clean separation is not fundamental. Space and time are woven together into one structure, and gravity affects both together. A useful place to begin is with the idea of motion itself. In the older Newtonian picture, motion happens through space while time ticks steadily in the background. The same for everyone, everywhere. Gravity changes motion by exerting a force. In Einstein's picture, there is no fixed background of that kind. Objects move through space-time, not just through space. Every object traces out a path that includes both where it is and how it moves from moment to moment through time. That path is sometimes called a world line, though the name sounds grander than the concept needs to be. It is simply the object's history through space-time. Now, in a universe without gravity, or at least in a region where space-time is effectively uncurved, the natural paths are the relativistic equivalence of straight lines. An object left alone moves along one of those paths. Nothing strange there, but introduce mass and energy, and the structure changes. The natural paths are no longer arranged the same way. What counts as straight through space-time is no longer what common sense expects from flat geometry. That is the heart of gravity in general relativity. Mass and energy do not reach out and tug. They alter the geometry through which motion unfolds. This is where explanations often become tempted by visual analogies, and some of them are helpful up to a point. People like to imagine a heavy object pressing into a stretched surface, with smaller objects moving along the resulting shape. That can hint at the idea that geometry matters, but it also brings problems because it makes it seem as though gravity is explained by another gravity acting downward on the sheet. So it is better to treat such analogies carefully and not ask too much of them. The deeper point is not that space is like rubber. It is that geometry can be different from place to place, and motion follows that geometry. Perhaps the cleanest way to understand this is to focus on time for a moment, because the role of time is what makes Einstein's picture richer than any merely spatial analogy can capture. Near a massive object, time runs more slowly than it does farther away. This is not a figure of speech. It is a real physical effect. A clock closer to a massive body ticks more slowly than a clock farther from it, all else being equal. That means gravity is not only shaping motion through space, it is shaping the rate at which time itself is experienced. This matters enormously, because if time flows differently in different places, then the natural paths through space-time will not behave the way they would in a world where time is uniform. Objects are always moving through time. Even when you feel spatially still, you continue along your path through time. So if the structure of time varies with position in a gravitational field, then the total geometry of space-time changes in a way that affects motion. Gravity is not just curved space, it is curved space-time. A helpful way to think about this without drifting into empty abstraction is to imagine two clocks, one higher up and one lower down in a gravitational field. The lower clock runs more slowly. That means the structure of time is different at those two locations. If you had enough patience and absurdly good clocks, you could compare them and see the difference directly, and we have done exactly that. This is not speculative or philosophical. It is measurable. In fact, modern technology depends on taking it seriously. But even before we get to practical consequences, the conceptual point is enough to change everything. Mass affects duration. It changes how time itself is laid out. Once that is accepted, the idea that objects follow curved paths no longer seems like a decorative oddity. It becomes unavoidable. If space-time is the arena in which motion happens, and if mass changes the arena, then natural motion changes too. A freely moving object follows the shape that space-time provides. Near the Earth, that natural path carries an unsupported object inward. Near the Sun, it guides planets into orbital motion. Near more extreme masses, the geometry becomes stronger and stranger, but the principle is the same. Matter and energy reshape the structure. Motion follows suit. There is a useful everyday comparison here, though like all comparisons, it only goes so far. Imagine walking through a city where the roads are laid out in a certain way. Your route is not determined just by your intentions. It is constrained by the streets, the corners, the bridges, the dead ends, and the oddly placed construction work that seems to have been there since the invention of disappointment. In a very simple city with perfectly straight roads, movement is easy to picture. In a city with winding streets, changing elevations, and one-way systems apparently designed by a trickster, the natural path from one place to another becomes less obvious. Space-time geometry is something like the layout of that city. Objects move according to what the structure allows. Mass changes the layout. Now, one might ask why time has to be involved at all. Why not just say that mass curves space and leave it there? The answer is that doing so would miss the full behaviour of gravity, especially when we want to explain why freefall is natural and why clocks behave differently near massive bodies. If only space were curved while time remained untouched, the theory would not produce the right physical results. Einstein's great achievement was to realise that the geometry of gravity is four-dimensional in the sense that spatial directions and temporal duration are part of one connected whole. That is why the theory can explain both motion and timing in one framework. This is also why gravity influences light. In Newton's language, force acts on mass. Light, as later physics made clear, does not fit comfortably into that old simple picture of little masses being pulled around. But in Einstein's theory, light follows the geometry too. It travels along the natural paths available in space-time. If space-time is curved near a massive body, then the path of light bends. The light is not being tugged by a force in the ordinary sense. It is following the shape of the world it moves through. That is a profound unification. It means that planets, falling apples, orbiting satellites, and beams of light all respond to gravity in the same broad geometric way. They follow paths determined by space-time structure. The details differ, of course. Light always moves at its characteristic speed locally. Massive objects can move more slowly. Their paths are not identical. But the underlying principle is shared. Geometry does the guiding. There is something very satisfying about that because it takes what used to seem like separate facts and reveals them as parts of one system. Why do clocks run differently near massive objects? Because time is part of the geometry that mass affects. Why do freely falling bodies accelerate downward? Because the natural paths through that geometry lead inward. Why does light bend near stars? Because the geometry itself is curved. Why can an orbit be understood without imagining a mysterious invisible pull that somehow reaches across empty space? Because the orbit is free motion in a curved space-time landscape. One framework, many consequences. Still, the idea can remain slippery unless we connect it more firmly to what you experience. So let us come back to the earth beneath your feet. When you stand on the ground, you are not simply in a place where something pulls you downward. You are in a region where space-time is shaped by the Earth's mass. The natural path for an unsupported object in that region is what we call free fall. Your body would follow that path if the ground were not there. But the ground is there, and it pushes on you, holding you off that path. That is why you feel weight. The feeling is local and mechanical. The reason for the path is geometric. This is where space and time working together becomes especially important. Your body is always moving through time. Even when you're standing still relative to the Earth, you're not static in space-time. You continue along your world line. The ground forces that world line to differ from the freefall one you would otherwise take. So standing on Earth is not merely a matter of occupying one place in space. It is a matter of being continuously guided along a different path through space-time than the one gravity alone would give you. The role of time in that story is not ornamental, it is essential. If time were the same everywhere, the geometry would not have the same structure. The Earth's mass changes the rate of time as well as the structure of spatial paths, and together those changes create the gravitational behaviour we observe. This is why general relativity is not just a theory of where things go. It is a theory of how the universe arranges both position and duration. One way to see how deeply this matters is to consider that even small differences in height can produce tiny differences in time. A clock on a mountain runs differently from a clock at sea level. The effect is tiny in ordinary circumstances, but real. If you could somehow live your entire life with one foot on a mountain peak and the other in a valley, which sounds uncomfortable and a little impractical, the time experienced at the two locations would not be exactly the same. That is how far Einstein's rewrite reaches. Gravity enters the very bookkeeping of time, and because time is involved, the curvature of space-time is not something one should picture as a static dent in a purely spatial fabric. It is dynamic and relational. Different observers can describe motion differently, but the geometric content remains. What matters is the structure that determines natural motion and clock behaviour. Mass and energy shape that structure. Not only heavy objects either. Energy in general contributes. A box of hot gas, for example, has more energy than the same box of cooler gas, and that energy matters gravitationally. This is one of the reasons Einstein's theory feels broader than Newton's. It does not merely say matter attracts matter, it says the content of the universe, matter and energy together, shapes space-time itself. That is also why the phrase mass bends space-time is useful, but slightly incomplete if taken too literally. It is not only mass in the narrow old sense. Energy, momentum, pressure and stress all contribute to the way space-time is shaped. The universe is not simply noticing how much stuff is present. It is responding to the full distribution of physical content. Again, this is one of those things that becomes mathematically exact in the full theory, but the conceptual point is enough for us here. The geometry responds to what is in the universe, and motion responds to geometry. The consequences become especially striking near very massive or compact objects. Around a dense star or a black hole, the distortion of space-time becomes extreme. Time slows more dramatically, paths curve more sharply, light can be bent strongly, and in the case of black holes there comes a point beyond which all future directed paths lead inward. That is not because there is a hook at the centre dragging things in. It is because the geometry becomes so strongly curved that the structure of possible motion itself changes radically. The paths available all point one way. That is a geometric statement before it is anything else. But even without going to such extremes, the basic lesson already changes the everyday world. The ground. Beneath you, the orbit of the moon, the timing of satellites, the bending of starlight, all of them belong to the same picture because space and time are bent together. This is what gives gravity its distinctive character. It is not just a matter of where objects are pulled. It is a matter of how the universe is shaped in the vicinity of mass and energy. There is a quiet elegance in that because it means gravity is not an extra mechanism laid on top of reality. It is woven into the structure of reality. Remove all matter and energy from a region, and space-time can be flat. Add matter and energy, and the geometry changes. No separate invisible chords are required. No hidden pushing fluid. No cosmic bureaucracy assigning attraction between objects. The geometry itself does the work. Of course, one should be careful not to make geometry sound mystical. Curvature here is not a poetic mood. It is a measurable physical feature with consequences for motion and clocks. We can test it. We can detect it. We can build systems that fail if we ignore it. That is one reason Einstein's theory became so important. It did not simply replace one mental image with another. It made new predictions and accounted for old puzzles with greater accuracy. The bending of time near mass is not a metaphor. It is part of the functioning world. There is also something slightly humbling about the way time enters the story. We are used to imagining that time is the one thing we cannot negotiate with. Clocks tick, hours pass, tea cools whether you're emotionally ready for it or not. Yet gravity shows that time is not as uniform as that intuition suggests. It has structure, it responds to mass, it joins space in the geometric life of the universe. So even the most ordinary act of waiting is, in a very deep sense, taking place inside a shaped space-time whose properties depend on the matter around you. Once that really settles in, the old idea of gravity as just a downward pull begins to feel almost charmingly undersized. It is not exactly wrong for daily life, but it leaves out too much. It leaves out the fact that time participates. It leaves out the fact that freefall is natural motion. It leaves out the fact that light bends because the geometry bends. It leaves out the reason clocks disagree in gravitational fields. And most importantly, it leaves out the deep unity of all these effects under one idea. Mass and energy shape space-time. Space-time shapes motion and timekeeping. That is gravity. And once we have that much in place, a great deal of the universe starts to look different. Light is no longer exempt. Clocks are no longer merely passive timers. Planets are no longer being hauled around by a force in the old simple way. They're all participants in the same curve structure. Which brings us naturally to the next step, because if space-time is bent by mass and energy, then we can begin to see why light, clocks, and planets all behave the way they do when they follow the curve. By the time we reach this point, gravity has already stopped looking like the simple downward pull most of us were taught to imagine. It has become something quieter and stranger. Mass and energy shape space-time. Free motion follows that shape. Weight comes from being prevented from following it. And once you accept all that, a new question begins to take over. If space-time is really the thing being curved, then why do such different things respond to that curve in ways that seem so coordinated? Why should a beam of light bend near a star? Why should a clock run differently on a mountain than at sea level? Why should planets keep tracing their patient long paths around the sun? What links all of those behaviors together? The answer is that none of them are exceptions. None of them stand outside the geometry. Light, clocks, and planets all follow the structure of space-time, because space-time is the structure within which their motion and timing make sense at all. That is the deep shift in Einstein's picture. Gravity does not sit beside the rest of physics as a separate pulling mechanism. It changes the stage itself. And once the stage changes, everything moving across it or measuring time within it must respond. It is worth beginning with the planets, because they are the most familiar example of graceful gravitational behaviour, and the one that probably feels least shocking at first. A planet circling a star looks like the sort of thing Newton already explained beautifully. The sun pulls on the planet moves forward. The result is an orbit. Clean, effective, and for many practical purposes entirely adequate. But in Einstein's view, the orbit is not best understood as a body being continuously tugged away from the straight path it would otherwise take through flat space. Instead, the orbit is what natural motion looks like in the curved space-time around the sun. That is not just a change in language, it changes what an orbit is. The planet is not being dragged around a corner by an invisible force in the old ordinary sense. It is following the straightest possible path available in a geometry that is not flat. That path, when viewed from the outside in ordinary spatial terms, looks curved, but the curvature is in the space-time, not in some separate force reaching out from the sun like a cosmic shepherd's crook. This helps explain why orbits feel so stable and so natural once established. The planet is not constantly fighting gravity and somehow managing to keep from falling. It is falling all the time, but in exactly the way space-time around the sun allows. It is free motion. The path closes around the star because of the geometry and the planet's speed through that geometry. In Newton's language, the sun pulls and the planet keeps missing. In Einstein's language, the planet follows the geodesic structure of the space-time around the sun. The two descriptions often agree closely enough that daily astronomy remains untroubled, but the deeper picture has changed. This matters especially when the orbit is not quite what Newton would expect. Mercury is the famous example. It moves closer to the Sun than the other major planets, and because of that, it explores a region where the curvature of space-time is stronger. Newton's theory gets Mercury's motion almost right, which is an impressive thing to say about a theory written centuries ago. But almost right is not the same as right. There was a small extra shift in Mercury's orbit that refused to disappear. Einstein's theory accounted for it naturally. That was one of the great early signs that planets do not merely respond to a force between masses. They respond to the geometry of space-time itself. Still, planets are large, slow, and old friends of gravity. Light is where the story becomes especially striking, because if you grow up imagining gravity as a pull between masses, you might reasonably wonder why light should care about gravity at all. Light has no rest mass in the way ordinary objects do. It does not sit still and weigh things down. It travels at its characteristic speed and refuses all invitations to behave like a dropped stone. So why should a beam of starlight passing near the Sun bend? In Newton's framework, one could attempt partial answers of various kinds, but Einstein's theory makes the reason much cleaner. Light follows the geometry too. It travels along the natural paths available in space-time. If space-time is curved near a massive body, then the path of light through that region is curved as well. The light is not being grabbed or slowed in some mechanical way by a little force hooked onto it. It is moving through a geometry whose straightest available routes are not the same as they would be in flat space-time. That is one of the most elegant things about general relativity. It extends the meaning of gravity beyond heavy objects. The same geometry that guides falling apples and orbiting planets also guides light. That means the bending of light near stars is not an add-on or an exception patched awkwardly onto the theory. It is exactly what should happen if gravity is geometry. Once you say that mass and energy curve space-time, you are committed to the idea that anything moving through space-time, whether a planet or a photon, must respond to that structure. This gives rise to one of the most beautiful observations in modern physics. When light from a distant star passes near the Sun, its apparent position in the sky shifts slightly, because the path of the light has bent on the way to us. This was one of the great early tests of general relativity, and it mattered not just because Einstein's numbers were right, but because the result itself said something profound. Even light does not travel through gravity as if gravity were merely a force acting on heavy things. Light travels through curved space-time. That is a larger and stranger claim, and once light bends, the universe acquires some wonderfully odd habits. Massive objects can act as lenses. Not glass lenses, of course, but gravitational ones. A galaxy or cluster of galaxies can bend light from more distant objects behind it, producing arcs, distortions, and even multiple images of the same source. It is one of those phenomena that sounds almost too theatrical to be real, as though the universe briefly decided to experiment with optical tricks. But it follows directly from the idea that light obeys geometry. If space-time is curved by mass, then paths of light curve too. The cosmos becomes its own lens maker. Now clocks seem at first like a very different case. A clock is not flying across the heavens or streaking through the void. A clock is a device that ticks. It measures duration. It minds its own business. Why should it care about curved space-time? The answer is that time is part of space-time, and a clock is a machine for tracing time locally. It is not outside the geometry. It is a participant in it. This is perhaps the hardest shift to make intuitive, because we're used to treating time as uniform. 1 second is 1 second. A minute is a minute. A clock in the valley and a clock on the hill ought to agree unless one of them is damaged or dramatic. But gravity does not leave time alone. Near a massive object, time runs more slowly. A clock deeper in a gravitational field ticks more slowly than one farther out. So the clocks are not merely telling us something about time in a pre-existing neutral universe. They're revealing the geometry of time itself. Imagine two identical clocks, one at sea level, and one high up on a mountain. Left to run and then compared carefully, they will not agree perfectly. The higher clock runs slightly faster. This is not because mountain air improves punctuality. It is because the clock higher up is in a region where the gravitational effect on time is weaker. The difference is tiny but real, and what makes it so important is that this is not some technical oddity affecting only the rarefied world of specialists. Modern navigation systems must account for it. Satellites orbiting the Earth are higher up and moving quickly, so both gravity and motion affect their clocks. If those effects were ignored, the system would drift badly. Phones would misjudge where you are. Maps would lose their confidence. Cars would become much less sure of which road they were on, which is already a fragile enough state of affairs without adding relativity to the problem. So clocks follow the curve not because they move like planets or fly like light, but because they measure one part of the geometry that gravity alters. A clock does not bend in space the way a beam of light does, yet it still responds to curved spacetime because time itself is part of the curve. A clock carried along one path through spacetime accumulates time at a certain rate. A clock on a different path, or in a different gravitational environment, accumulates it differently. That is why the role of time in general relativity is so essential. If gravity affected only space, clocks would remain dull, but they do not. They become evidence. There is also a deeper unity here. A planet follows a geodesic through curved space-time. Light follows its own natural space-time path through that same curved geometry. A clock, meanwhile, measures how much proper time accumulates along a path through space-time. Different paths and different regions produce different results. These are not three unrelated stories. They are three aspects of the same underlying structure. Motion, light propagation, and timekeeping are all tied to geometry. This is what makes Einstein's view feel so satisfying once it settles in. It does not just explain one phenomenon at a time, it brings several apparently different things under one principle. Why does Mercury's orbit precess a little more than Newton expected? Why does starlight bend near the sun? Why do satellite clocks need correction? The answer in each case is not a separate patch or a new force or a special privilege for one type of object. The answer is curved space-time. That word curved can still sound misleading if one imagines only bent lines in space. So it is worth making the point again in a more grounded way. Curvature means that the relationships of distance, time, and natural motion are different from what they would be in a flat space-time. It means straightest paths are not, globally, what ordinary flat intuition would predict. It means clocks in different places or on different trajectories do not necessarily agree. It means light rays passing near mass do not keep the same apparent direction they would have kept in the absence of curvature. It means planetary orbits have subtleties that only a geometric account gets exactly right. Curvature is not decoration. It is structure. And because it is structure, it shows up everywhere once you know how to look. Tides, for example, are part of this story too, though they often get introduced in more familiar language. The moon does not pull equally on every part of the Earth. The geometry of the gravitational field varies from place to place. Different regions of Earth follow slightly different tendencies in space-time, and the result is stretching. Oceans respond visibly because they are fluid and generous with their compliance. The Earth itself responds too, though more modestly. Tides are one of the many ways gravity reveals that it is not merely a uniform downward command, but a structured field of differing effects across space. The same is true in a more dramatic register for gravitational waves. When very massive bodies move violently, such as black holes spiraling together, they do not merely influence nearby objects through some static pull. They disturb the geometry itself. Ripples propagate outward through space-time. If gravity were only a conventional force in the old sense, this would be harder to make sense of. But if gravity is geometry, then changing mass distributions can produce travelling changes in geometry. Space and time themselves ripple, and astonishingly, we have detected those ripples. The world became strange enough to include measurable murmurs in space-time, and we built instruments delicate enough to hear them. Still, For all the grandeur of distant stars and colliding black holes, the idea remains closest to home when we remember what it says about the simplest situations. A clock on your wall is not quite as innocent as it looks. A beam of light crossing a room is, in principle, participating in the same geometry that guides light past galaxies. The earth beneath your feet is shaping the space-time that determines what counts as straight motion near the ground. The curve is not only out there in exotic astrophysical environments, it is here, though usually gently enough that daily life can continue, without anyone needing to announce it over breakfast. That gentleness is why Newton remains so useful. In weak gravitational fields and at ordinary speeds, the curved geometry can often be approximated by the older language of force with remarkable success. That is why planets still look as though they are pulled around stars, why falling objects still seem to accelerate downward under a force, and why most of us can get through the week without correcting our schedules for altitude. But the deeper truth remains available whenever we need greater precision or wider understanding. The force picture is a good practical shorthand. The geometry picture is the fuller account. There is a kind of quiet democracy in that. Light, clocks, planets, satellites, apples, and people do not each negotiate separate private deals with gravity. They all live in the same curved space-time. Their different behaviours come from how different things move through that common structure, not from gravity changing its mind depending on the audience. A planet traces an orbit because of the shape of the space-time around a star. Light bends because of that same shape. A clock runs differently because time is part of that same shape. One geometry, many consequences. It is also worth noticing how this changes the meaning of prediction. In Newton's world, you ask what force acts, and then compute the resulting motion. In Einstein's world, you ask what geometry is present, and then determine the natural paths and timing within that geometry. That is not a small stylistic preference, it is a reorganization of the question. Instead of thinking of the universe as a collection of objects being pushed and pulled within a fixed arena, you think of it as a dynamic structure in which matter and energy shape the arena, and motion emerges from that shaped structure. That is why light, clocks and planets follow the curve. They have no alternative. The curve is not an obstacle placed in their way. It is the local form of reality they inhabit. Light does not decide to bend out of politeness. Clocks do not slow down out of caution near a massive body. Planets do not orbit because they have entered into some old ceremonial agreement with the sun. They behave as they do because space-time has been shaped by mass and energy, and that shape governs motion and duration alike. Once you become comfortable with that, many of the classic tests of general relativity begin to look less like isolated triumphs and more like different windows onto the same truth. Mercury's orbit, the bending of starlight, the timing corrections in satellites, all of them say the same thing in different accents. Gravity is geometry. The curve is real, and the objects and signals moving through the universe reveal that reality in their own ways. Which means the next step is to look more directly at those pieces of evidence in the sky and in our technology, because once the theory says what should happen, the real drama lies in seeing the world agree. By the time a scientific idea reaches the level of changing how we describe reality itself, admiration is no longer enough. Beauty does not suffice. Elegance does not suffice. A theory may be clever, neat, and strangely satisfying, but sooner or later the universe has to be asked a simple question. Is this actually how you work? And in the case of Einstein's view of gravity, that question mattered all the more because the new picture was so bold. It did not merely adjust Newton's account of falling bodies and orbiting planets. It said that gravity was not fundamentally a force in the ordinary sense at all. It said that mass and energy shape space-time, that free motion follows that shape, and that what we feel as weight is the resistance to falling rather than the direct sensation of gravity itself. That is the sort of claim that cannot survive on charm. It needs evidence, not vague hints, not philosophical satisfaction, Real tests, real measurements, the kind of stubborn observational agreement that turns an audacious idea into a serious description of the world. And this is where the sky became the testing ground. Because once Einstein had rewritten gravity in terms of curved space-time, the heavens offered several chances to see whether the universe agreed. Mercury gave one of the first clues, starlight gave another, and as the years passed, the evidence above us kept accumulating, each piece reinforcing the same strange message. Gravity is geometry. Let us begin with Mercury, because there is something almost endearing about the fact that one of the earliest cracks in Newton's great theory came from the smallest major planet in the solar system. Mercury is not especially large. It does not dominate the sky. It is difficult to observe compared with brighter and more accommodating planets. It stays close to the sun from our point of view, which means catching it often requires some care and some patience, and perhaps a willingness to accept that astronomy occasionally involves a great deal of peering at places in the sky that seem determined to be unhelpful. And yet Mercury turned out to matter enormously. For centuries, Newton's gravity had described planetary orbits with astonishing success. If you wanted to know how planets moved around the sun, Newton was your man. His theory explained why the planets followed the paths they did, and why those paths took the form of ellipses rather than perfect circles. It unified the Earth and the heavens under one rule. That success was so profound that any deviation from it had to be approached with caution. If a planet failed to behave exactly as expected, the first assumption was not that Newton was wrong. The first assumption was that perhaps something else had been overlooked. Another planet, perhaps. Some additional matter, a measurement problem, a modest error somewhere in the bookkeeping. Mercury, however, kept being slightly awkward. Its orbit is not fixed in space. Like the orbits of other planets, it slowly shifts over time. The point of closest approach to the Sun moves gradually around. This effect is called precession, though one need not dwell too heavily on the term. The important point is that the orbit slowly rotates. Newtonian gravity, once the effects of the other planets were included, could explain nearly all of that shift. Nearly all. But not quite. There remained a small leftover amount, a tiny extra advance that refused to disappear. It was not large enough to ruin Newton's theory in any practical sense. No one was watching Mercury fly off in protest, but it was large enough to be real, and small stubborn discrepancies are often where physics starts to become interesting. People tried to explain it. Perhaps there was another planet closer to the Sun, an unseen object tugging on Mercury and altering its motion. This hypothetical world was even given a name, because science is nothing if not optimistic in the face of incomplete evidence. But the planet did not oblige by appearing. The discrepancy remained, and for years it sat there as one of those mild but persistent irritations that great theories occasionally develop. Rather like a once dependable cupboard door that has decided it no longer closes properly, but only when guests are over. Then Einstein arrived with general relativity, and Mercury's little misbehaviour suddenly stopped being an irritation and became a clue. In Einstein's picture, Mercury was not moving through a simple Newtonian force field. It was moving through the curved space-time near the Sun. Since Mercury travels closer to the Sun than the other planets, it explores a region where the curvature is stronger. The geometry there is not quite what Newton's framework assumes. And when Einstein worked out what general relativity predicted for Mercury's orbit, the missing amount appeared, not by adding a new planet, not by introducing some emergency patch, but naturally as a consequence of the theory itself. That mattered enormously. It meant that Einstein's theory was not merely a different way of talking about gravity. It was quantitatively better where the old theory strained. Mercury did not prove general relativity all by itself, because science is rarely so courteous as to let one measurement settle everything in a single dramatic flourish. But Mercury was one of the first strong signs that something real had changed. Space-time curvature was not just a clever reinterpretation. It could account for a stubborn piece of the solar system more precisely than Newton's invisible pull. There is something satisfying about that because Mercury is not exotic. It is not a black hole or a hypothetical cosmic monster, or some remote object only visible through heroic feats of instrumentation. It is a planet in our own solar system, one that had been watched for generations. The first strong hint that gravity might be geometry came not from some bizarre corner of the universe, but from a familiar world tracing a path that was just a little too subtle for the old theory. Still, Mercury was only part of the story. If general relativity was right, it had to do more than repair a small planetary discrepancy. It had to make new predictions. One of the most famous involved light itself. This was a bigger deal than it may sound at first. In the Newtonian picture, gravity acts between masses. That works beautifully for apples and planets, and people who have made unfortunate decisions involving ladders. But light does not fit so comfortably into the idea of a force between masses. Einstein's theory handled this much more naturally. If gravity is the curvature of space-time, then light should follow the curvature too. A beam of starlight passing near a massive body such as the sun should bend. Not because the sun reaches out and grabs the light in the old ordinary sense, but because space-time near the sun is curved, and light follows the natural paths available within that curved geometry. That prediction was simple enough to state, and awkward enough to test. Normally the sun's brightness overwhelms the stars behind it, making it impossible to see whether their apparent positions shift when their light passes near the sun. The solution was to wait for a total solar eclipse, when the moon blocks the sun's bright disk and the stars around it can briefly be observed. If Einstein was right, the stars seen near the eclipsed sun should appear slightly displaced from where they would normally be. It is one of those moments in science that has become almost mythic, and with some reason. In the year 1919, expeditions observed a total eclipse and measured the positions of stars near the sun. The result was consistent with Einstein's prediction. Starlight bent. The shift was small, as many of the most important things in physics insist on being, but it was enough. The sky had offered a direct answer. Light did not travel past the sun as though space-time were flat and gravity merely a pull between masses. The geometry mattered. The path curved. Now, history being what it is, the details of those observations and their uncertainties have been discussed and re-examined many times since, which is exactly as it should be. Science is not improved by turning measurements into fairy tales, but the broader point survived and has been confirmed far more precisely over the decades. Light bends near massive objects. The sky does what general relativity says it should do. That effect is not confined to eclipses either. Once astronomers had better tools, they found the same principle at work on much larger scales. Massive galaxies and clusters of galaxies bend light from more distant objects behind them. The result can be extraordinary. A single distant galaxy may appear stretched into arcs. One object may show up in multiple places because its light has travelled to us along different curved paths. The effect is called gravitational lensing, and it is one of the clearest demonstrations that space-time geometry is not a metaphor. The universe really does redirect light through its own structure. There is something wonderfully practical about this too. Astronomers now use gravitational lensing as a tool. It helps reveal mass distributions in galaxies and clusters. It provides clues about matter we cannot see directly. It even helps us look deeper into the universe by magnifying distant objects. So a prediction that began as an elegant consequence of curved space-time has become part of the working toolkit of modern astronomy. The sky does not merely tolerate Einstein's theory, it assists with it. And then there is time. If mass bends space-time, then time itself must be affected, not just the paths of objects and beams of light. We have already touched on that idea, but evidence in the sky makes it more concrete. Light climbing out of a strong gravitational field loses energy in a way that changes its frequency. This is known as gravitational redshift. though again the terminology matters less than the idea. Light emitted near a massive body arrives, altered because time itself runs differently there. That is a subtle effect, but it has been observed. The spectra of light from dense stars show it. The timing of signals and gravitational fields shows it. The sky, once again, behaves as though time is part of the geometry. This is one of the reasons white dwarfs and neutron stars became especially interesting to physicists. These objects pack a great deal of mass into a relatively small region, producing strong curvature. They're useful laboratories for relativistic gravity, because the effects are more pronounced than they are around an ordinary star such as the Sun. Light escaping from them carries the fingerprints of gravity's effect on time. Their environments reveal a universe in which clocks and signals do not behave as they would in a flat Newtonian stage. There is also a related effect involving the travel time of light or radio signals near a massive object. If space-time is curved, signals passing near the Sun do not simply cross empty space at the same rate they would in flat geometry. Their journey takes slightly longer than one would otherwise expect. This is sometimes called the Shapiro time delay, though the label is less important than the image. Even the timing of a signal's trip across space is altered by gravitational curvature. The path is not just bent. The structure of time along the route is changed as well. Once more, the evidence points in the same direction. Gravity is not merely a pull on moving bodies, it is a modification of space-time itself. If you step back and look at these pieces together, the pattern becomes hard to ignore. Mercury's orbit says that planetary motion near strong curvature is not perfectly Newtonian. Starlight near the Sun says that light follows curved space-time. Gravitational lensing says that whole galaxies and clusters reshape the appearance of the sky by redirecting light. Gravitational redshift says that time behaves differently near massive objects. Signal delays say that even the travel time of light responds to geometry. Each test differs in detail. Each uses different objects, different instruments, and different methods. But all of them converge on the same message. This is one of the marks of a powerful theory. It does not succeed in one narrow corner only. It succeeds across very different situations because the underlying principle is deeper than any one example. General relativity explains Mercury, not because Mercury is special, but because Mercury explores curved space-time near the Sun. It explains bent starlight, not because stars are cooperative, but because light follows geometry too. It explains time shifts, not because clocks have developed personalities, but because time is part of the structure, mass, and energy effect. There is also a cultural side to this story that is worth pausing on briefly. Newton's picture of gravity is so intuitive that even after Einstein, most of us still default to it in casual thought. We say the Earth pulls us down. We say the Sun pulls the planets, and that is perfectly fine as shorthand. No one needs to explain geodesics while handing someone a dropped spoon. But the sky has made clear that the shorthand is not the deepest story. The deepest story is that massive bodies alter space-time, and motion, light, and clocks reveal that alteration in different ways. What is especially lovely is that the evidence often comes from things that seem so calm. A planet orbiting quietly, a star's light slipping past the Sun, a distant galaxy appearing in a strange arc, a signal taking slightly longer than expected. None of these announce themselves with great drama to the naked eye. The universe is not shouting. It is whispering in precise deviations, small shifts, subtle timings. Science, at its best, is often the art of learning how to hear those whispers. And this is where Einstein's rewrite of gravity proved itself. Not through a single overwhelming spectacle, but through a series of stubborn agreements between theory and sky. Each one on its own might seem modest. Together they become decisive. The sky behaves as though gravity is geometry. Of course, evidence in astronomy has a particular charm because it lets us test grand ideas against the heavens themselves. But there is another side to the story, one that brings relativity much closer to home. because the same theory that explains Mercury's orbit and the bending of starlight also affects technologies we use in ordinary life. The same curvature that shows up around the Sun and in distant galaxies also matters for satellites circling the Earth. And the same geometry that alters the path of light from stars can ripple through the universe in waves when enormous masses collide. So after the sky helped confirm Einstein's idea, the modern world and our instruments began confirming it in an even more direct way. And that is where the story naturally goes next, from Mercury and starlight to GPS systems, gravitational waves, and the increasingly practical business of living inside curved spacetime. One of the easiest mistakes to make with a theory as strange as general relativity is to imagine that it belongs safely far away from ordinary life. It can seem like the sort of subject that lives only in observatories, textbooks, and the minds of people who enjoy thinking about black holes before breakfast. Curved space-time, bent light, clocks slipping out of sync near massive objects, all of that sounds grand and distant enough that it is tempting to place it in the category of interesting cosmic business, with no immediate effect on the rest of us. The stars can keep their geometry. The planets can keep their elegant paths. Meanwhile, down here on Earth, we can get on with finding our keys and pretending we remember where we parked the car, but gravity has a way of refusing to stay in the heavens. If Einstein was right, then the geometry of space-time is not just a remote curiosity. It affects the world we live in and the technologies we use, and that is exactly what we find. The same theory that explains Mercury's orbit and the bending of starlight also quietly shapes modern navigation. The same idea that says mass-curved space-time also predicts that space-time can ripple, and those ripples, astonishingly enough, have been measured. So what once sounded like a radical reinterpretation of gravity has become something more than an elegant theory. It has become part of the operating manual for reality. A very good place to begin is with GPS, because it is one of those things most people use without spending much time wondering how absurdly difficult it actually is. You open a map on your phone, and within moments a little marker announces where you are with an air of confidence that is often impressive and occasionally insulting. It tells you when to turn, how long the journey will take, and sometimes, in a tone of mild disappointment, that you have ignored perfectly good advice and chosen a worse route. All of this feels so routine now that it is easy to forget how improbable it really is. For a navigation system like that to work, it needs timing of extraordinary precision. The basic idea is simple enough in principle. Satellites orbit the Earth and broadcast signals. Your device receives signals from several of them and compares the timing. Since the signals travel at a known speed, the device can infer how far away each satellite is. Combine those distances carefully, and your location can be determined. That all sounds calm and manageable until you remember that light and radio signals move very fast indeed, which means that even tiny timing errors become significant distance errors. A small mismatch in the clocks can shift a location by kilometers. That is not a minor inconvenience. That is the difference between turning left at the next road and driving serenely into a lake while insisting that the system told you it was fine. So the clocks in the satellites matter enormously, and this is where relativity stops being a distant theory and becomes a practical necessity. Those clocks do not tick at the same rate as clocks on the ground. They cannot. The satellites are moving quickly relative to the Earth, which brings in the time effects of special relativity, and they are also higher up in the Earth's gravitational field, where gravity is weaker, which brings in the time effects of general relativity. These two influences do not cancel in a convenient way. They combine to produce a real difference in how time passes for the satellite clocks compared with clocks on Earth. This is one of those facts that deserves a quiet moment because it is wonderfully strange. The little navigation system in your pocket works properly only because engineers account for the fact that time flows differently in orbit than it does on the ground. If they ignored Einstein and trusted a simpler Newtonian picture of gravity with perfectly uniform time, the system would drift badly. It would not fail in some dramatic cinematic flash. It would fail in the more ordinary and more annoying way that many technologies fail by becoming steadily wrong. And it would become wrong very quickly. The relativistic timing differences are not large enough to ruin breakfast, but they are easily large enough to ruin navigation. So before the system can be trusted, the clocks must be corrected. In other words, general relativity is not merely compatible with GPS, it is built into it. Every successful route calculation, every delivery made to the right address, every person who manages to find a hotel in a city they have never visited before, all of them benefit from the fact that gravity is not just a pull between masses, but a geometry affecting time itself. There is something very satisfying about that because it ties one of the strangest scientific ideas directly to ordinary experience. You do not need a black hole or an eclipse, or a century of astronomical data to see relativity matter. You need a phone, a satellite network, and a willingness to let physics quietly improve your sense of direction. Einstein's theory is there in the timing, working behind the scenes, making sure the world you move through is described accurately enough for modern life to function. It also reinforces the central point we have been tracing all along. Gravity is not simply about objects being drawn downward, it is about the shape of space-time. Satellites are not exempt from that shape just because they carry clocks and electronics instead of philosophical significance. Their motion and their timing both respond to the Earth's gravitational geometry. The fact that this must be accounted for in a practical machine is a rather decisive answer to anyone tempted to treat relativity as intellectual decoration. And then there are gravitational waves, which take the story in a different direction, but deepen the same idea. Once gravity is understood as geometry, a very natural question emerges. If mass and energy can curve space-time, and if changing conditions in space-time affect motion and time, then can that geometry itself carry disturbances? Can the shape of space-time ripple? According to general relativity, yes. When massive objects accelerate in certain ways, especially in violent and asymmetric motions, they can produce waves in space-time that travel outward. These are not waves in a material medium like water or air. They are changes in the geometry itself, moving through the universe. Distances stretch and squeeze by tiny amounts as the wave passes. Time and space, already joined in relativity, participate together in the disturbance. That is a very strange claim. It means that gravity is not just a static feature of the environment around masses. It can be dynamic. The geometry can change and those changes can propagate. In the Newtonian picture, gravity acts as a force between masses, and while one can talk about varying gravitational effects, the concept of space-time itself rippling does not naturally arise. In Einstein's picture, however, it follows with beautiful logic. If gravity is the geometry of space-time, then changing mass distributions should sometimes produce travelling changes in that geometry. The difficulty is that these waves are incredibly faint by the time they reach us. Even events involving enormous masses such as black holes colliding or neutron stars spiralling together produce distortions that are tiny when they finally sweep across the Earth. Detecting them is one of the great experimental achievements of modern science, not because the idea was fanciful, but because the measurement problem was so brutally demanding. Space-time does not rumble loudly when a wave passes. It shifts by amounts so small that even describing the precision involved begins to feel slightly absurd. Yet we did detect them. Instruments were built to measure the minute stretching and squeezing caused by a passing gravitational wave. They do this by comparing the travel of light along long paths arranged with extraordinary care. If space-time itself changes shape even by a minuscule amount, the pattern of light shifts in a way that can be measured. It is one of those triumphs that feels almost indecently clever. Einstein says geometry can ripple. Humanity responds by building machines delicate enough to notice when the universe twitches. The first direct detection of gravitational waves was a historic moment not only because a prediction had been confirmed, but because it revealed something profound about reality. We were no longer merely inferring curved space-time from planetary orbits or bent starlight or corrected satellite clocks. We were directly detecting changes in space-time geometry passing through the Earth. Not force fields in the old ordinary sense, not particles bumping into detectors in the familiar way. Geometry itself, dynamic and physical, arriving from a distant cosmic event. That event came from black holes spiraling together and merging, which already sounds like the sort of thing science fiction would have overused long ago if the universe had not quietly done it for real. Two immensely massive objects orbiting each other lose energy through gravitational radiation, draw closer, circle faster, and eventually collide. The final stages are spectacular in energetic terms, and the resulting space-time waves spread outward across the cosmos. By the time they reached Earth, they were tiny. But tiny is not the same as absent. The instruments listened, and space-time answered. That matters because gravitational waves are not just another test among many. They confirm the dynamic part of Einstein's picture. Gravity is not simply the static curvature around a planet or a star. It is a living geometry that can change, interact, and transmit information about violent events across the universe. Black holes can announce themselves not only through light from surrounding matter, but through the very structure of space-time. Neutron stars can collide and send out both electromagnetic signals and gravitational waves, giving astronomers a richer account of what happened. A new kind of astronomy opens up, one that does not rely only on light. There is something deeply satisfying in that as well. For most of human history, the heavens were known through sight. Then we expanded our senses with radio, infrared, ultraviolet, X-rays, and other parts of the spectrum. Now, with gravitational waves, we gain access to a different kind of signal altogether. We're no longer only looking at the universe. In a sense, we are listening to the movement of space-time. Not sound, literally, because sound requires a medium like air, and space is not generously filled with that. But the analogy captures something important. The universe has new ways of speaking to us once gravity becomes geometry, rather than merely force. And all of this reinforces the shape of reality in a very literal sense. It is not only that space-time can be curved, it is that the curvature is measurable, active, and consequential. GPS reveals that time itself is part of the gravitational structure. Gravitational waves reveal that the structure is dynamic. Together they show that general relativity is not confined to edge cases. It governs both the silent precision of satellite timing and the violent drama of colliding black holes. That range is one of the most impressive things about the theory. It handles the ordinary and the extreme without changing its basic principles. The same geometric view of gravity explains why clocks in orbit need correction, and why immense cosmic mergers send ripples across the universe. One could hardly ask for a clearer sign that the theory has hold of something fundamental. It does not merely perform well in one corner. It performs across scales that differ so vastly they almost feel like separate worlds. There is also a quiet philosophical consequence to all this, though one need not become too solemn about it. The word reality is often thrown around with an air of confidence that exceeds our actual understanding. We say things are real because they are tangible, visible, immediate. A chair is real. Rain is real. A missed train is real in a particularly rude and memorable way. Curved space-time, by contrast, can sound conceptual, mathematical, perhaps even faintly decorative. But GPS and gravitational waves force a reassessment. If a thing alters clock rates, redirects light, changes orbits, and ripples through detectors on Earth, it is not merely a convenient abstraction. It belongs to the furniture of the world, even if it is not the sort of furniture one can sit on. This is part of what science does at its best. It enlarges the category of what counts as physically real. At first, geometry may seem too austere, too mathematical, to deserve the same standing as matter or motion. But once geometry begins affecting clocks, satellites, light, black holes, and navigation systems, the distinction begins to soften. The shape of space-time is not a way of talking about gravity from a safe distance. It is gravity in the sense that matters most physically. You can see this in the way the theory changes our instincts about what is fundamental. In an older picture, one might think the core ingredients are matter, space, time, and forces, all separately identifiable. Matter sits in space. Time flows. Forces act. In general relativity, the separation is less clean. Matter and energy influence space-time. Space-time influences motion and timing. The architecture and the contents are linked. The stage is not indifferent to the actors, and the actors do not move without altering the stage. Reality becomes more relational than the old mechanical picture suggested. That does not make it vague, quite the opposite. The theory is precise, demanding, and testable. But it does make reality stranger. The world is not built from objects alone, nor from forces laid between them like hidden strings. It is built from objects, energy, motion, and geometry all tied together. That is why the title of our little exploration keeps proving itself. Gravity does not work the way you think. Not because common sense is foolish, but because common sense evolved for falling fruit and uneven pavements, not for the architecture of space-time. There is another pleasant irony in the role of GPS. People often imagine that relativity belongs to the rarefied world of advanced science, while everyday technology belongs to practical engineering. In truth, the two are often inseparable. The practical works because the theoretical is right. Engineers do not correct satellite clocks out of loyalty to Einstein, or because it seems stylish to do so. They do it because the system would not work otherwise. The geometry of space-time enters the most unromantic corners of infrastructure. There is something almost comic about that. The theory that rewrote gravity now helps you find the nearest petrol station. And gravitational waves, for all their grandeur, also bring the universe into a more intimate relation with us. A black hole merger billions of light years away can alter distances on Earth by a tiny amount. Not enough for your sofa to notice, thankfully, but enough for an instrument to detect. The shape of reality is not sealed off into isolated local compartments. Events at unimaginable distances can send their geometric traces across the cosmos and through the ground beneath us. That is not mystical interconnectedness. It is physics, exacting and measured. But it is still a rather extraordinary thing to sit with. The more one reflects on it, the harder it becomes to treat general relativity as merely one theory among many. It is a framework that changes what we mean by gravity, by motion, by time, and even by physical influence. Newton's invisible pull was a magnificent achievement and remains wonderfully effective in many situations. But Einstein's geometry goes deeper. It tells us why clocks differ, why light bends, why free fall feels weightless, why Mercury was slightly awkward, why gravitational lensing occurs, why navigation systems need correction, and why space-time can ring with waves after catastrophic mergers. All of that from one reimagining of gravity. And yet even now, with GPS working quietly above us, and gravitational waves passing through us unnoticed until instruments intervene, there is still something unfinished about our understanding. General relativity is profoundly successful, but physics has a habit of remaining incomplete precisely where it is most beautiful. Questions remain about how gravity fits with the quantum world, about what space-time is at the deepest level, about whether geometry itself emerges from something still more basic. So even as the evidence piles up and the shape of reality grows clearer, the story does not settle into finality. It opens further, which makes the next step a natural one. After all the practical confirmations and cosmic detections, after seeing geometry appear in clocks, light, planets, and waves, we come back to the larger question that has been quietly following us from the start. If gravity is not a conventional force but the structure of space-time, then what does that really mean for how we should think about the world, about motion, and about our own place inside a universe where even standing still turns out to be a negotiated arrangement? By now, the old picture of gravity as a simple downward pull has had quite a lot to endure. It began as one of the most familiar ideas in daily life. Things fall, feet stay on the floor, tea stays in the cup unless you become overconfident with a tray. The Earth pulls downward, and that seemed to explain most of what anyone needed to know. It was tidy, it was useful, it was, for ordinary purposes, entirely serviceable. But once we followed the idea more carefully, it began to loosen. Weight turned out not to be the direct feeling of gravity itself, but the feeling of support. Freefall turned out not to be a state of violent force, but the closest thing to natural motion in a gravitational field. Standing still on the Earth became less like a neutral condition and more like a continuous interruption. Space and time, once treated as separate and dependable backgrounds, turned out to be linked, shaped, and altered by mass and energy. And so we arrive here with a rather different picture in hand. Gravity is geometry, not poetry, not metaphor, geometry. That may still sound slightly too mathematical to be satisfying at first, as though we have replaced one physical idea with a more elegant but less tangible one. A pull feels real. Geometry sounds like something from a classroom where triangles were drawn, with great confidence and occasionally very little joy. But Einstein's great insight was that geometry, in this case, is not merely a description we impose on reality from the outside. It is part of reality itself. The structure of space-time, the way distances and durations are arranged, the paths that count as natural motion, all of that has physical consequences. If the geometry changes, clocks change, light changes, orbits change, and the behaviour of matter changes with them. That is not abstract at all. It is as physical as anything can be. You can see why this matters by thinking again about the simplest situation of all. You're standing on the Earth. Nothing seems more ordinary. Perhaps you're in the kitchen. Perhaps you're at a window. Perhaps you're waiting for something in the oven and already suspecting you should have set a timer instead of relying on optimism. From the older point of view, gravity pulls you down and the floor stops you. From the deeper relativistic point of view, the Earth has shaped the space-time around it, and your natural path through that curved space-time would be free fall. The floor beneath you prevents that. It pushes upward. That push travels through your feet, legs, spine, and the rest of you. You experience that as weight. In other words, what feels most stable and ordinary in your life is already an encounter with geometry. There is something quietly wonderful about that. It means the grandest ideas in physics are not sealed away from daily experience. You do not have to orbit a neutron star or fall into a black hole to participate in the structure of space-time. You already are. Every step you take, every chair you sit in, every time you place a mug on a table and trust it to remain there, you are dealing with a universe in which gravity is not merely an invisible hand but the shape of the world around you. That changes how we think about motion. In ordinary language, motion and rest seem like opposites, cleanly separated. Something moves or it stays still. But relativity makes that contrast less fundamental than it first appears. The deeper question is not whether something changes position relative to the ground. The deeper question is whether it is following its natural path through space-time or being pushed away from it. A satellite in orbit, racing around the Earth at great speed, may be in freer motion than a person standing quietly by the sink. A dropped object may be more nearly unforced than a book resting politely on a shelf. The shelf, the floor, the chair, all these familiar things become agents of interruption. They are not merely passive supports. They are what keep matter from following the free paths that curved space-time offers. That, in turn, changes how we think about force itself. In the older picture, gravity joined the list of forces alongside pushes, pulls, and other influences that change motion. In Einstein's picture, gravity becomes different in kind. A wall pushing on your back and the Earth shaping space-time are not the same sort of thing. One is a local mechanical interaction that your body feels directly. The other is part of the structure within which free motion happens. This is why a person in free fall feels no gravitational force in the ordinary sense. There is no support pressing on them. No chair, no floor, no ground insisting on an alternative arrangement. They are simply moving naturally through the geometry. Once that is clear, the universe begins to look less like a machine made of objects, exchanging pushes and pulls across a fixed stage, and more like a dynamic structure in which the stage itself participates. Matter and energy do not merely move through space-time, they shape it, and space-time, once shaped, guides motion in return. That mutual relationship is one of the most important ideas in modern physics. The contents of the universe and the geometry of the universe are not separate stories. They are chapters of the same one, though mercifully without requiring anyone to do all the mathematics on a sleepless Tuesday evening. It also changes how we think about time. This may be the strangest part of all, because we are used to treating time as the one thing that simply keeps going no matter what else happens. A clock ticks, a day passes, bread goes stale, meetings run longer than they should. Time seems universal, steady, and indifferent. Yet gravity tells us otherwise. Near a massive object, time runs differently. Clocks higher up and clocks lower down do not remain perfectly in agreement. The Earth does not merely guide falling objects and orbiting satellites, it shapes duration itself. So when we say gravity is geometry, we are not just talking about curved paths through space. We are talking about the structure of time as well. That has a curious effect on how we see ourselves. Human beings live by time in a very intimate way. We wake, work, rest, remember, anticipate, schedule, regret, and promise, all according to temporal order. A theory that tells us time is not uniform everywhere is not merely making a technical remark. It is telling us that one of the deepest conditions of our experience is woven into the same geometry that governs planets and light. The clock on the wall and the orbit of the moon belong in that sense to one connected physical story. There is a certain humility in this. For a long time, science, often advanced by taking the world that humans directly experience and discovering that it is not central after all. The Earth is not the centre of the cosmos. The sky is not a perfect sphere arranged for our benefit. Matter is not solid in the way it first appears, and now gravity tells us that even our most immediate sense of up, down, stillness, and weight does not reveal the deepest structure directly. What feels obvious is useful, but not final. We live in a world our senses were not designed to interpret at the level of fundamental geometry. They were designed to help us not fall off things and not walk into trees. On that front they have done fairly well. On the matter of space-time they require assistance. And yet there is comfort in that too, because the universe does not become less real when it becomes less intuitive. In some ways it becomes more so. The chair supporting you is no longer just furniture. It is a surface exerting the force that keeps you from following your geodesic. The floor is not merely where the room happens to stop. It is the thing pushing you away from free fall. A scale does not secretly measure how beloved you are by the Earth. It measures support. A satellite does not circle above you because it has escaped gravity. It circles because it is surrendered to gravity in the form of free motion through curved space-time. The world becomes stranger, yes, but also more coherent. This coherence is one of the reasons Einstein's picture continues to feel so powerful. It takes things that seem unrelated and binds them together under one idea. Why do planets orbit? Why does Mercury's orbit shift a little more than Newton expected? Why does starlight bend near the sun? Why do clocks in satellites need correction? Why can space-time ripple when black holes collide? In an ordinary force picture, these become a collection of cases. In the geometric picture, they become different expressions of one structure. Curved spacetime explains them all, not by brute force, but by revealing that they were never separate to begin with. There is also something deeply human in the way this changes our sense of place. We often imagine ourselves as very small in the universe, and of course, in many ways we are. We live on a modest planet around an ordinary star in one galaxy among many. No theory of gravity is likely to flatter us into cosmic importance, but relativity gives us a different kind of dignity. It says that the same laws structuring the largest scales of the cosmos also shape the details of our ordinary lives. The curvature that bends light around galaxies also affects the timing in our navigation systems. The geometry that guides stars and black holes also explains why your feet feel tired after a long day. There is no special human scale at which physics suddenly becomes local and personal. The same reality runs through all of it. That can make daily life feel a little less provincial, not grand in an embarrassing way, just connected. When you stand by a bus stop in the rain, hoping the schedule is more honest than usual, you are not outside the deep story of the universe. You are in it. Your body is supported against free fall. Time is passing at the rate allowed by your position in the Earth's gravitational field. Light from the street lamps reaches your eyes, along paths shaped, however slightly, by the geometry of space-time. None of this makes the bus come faster, regrettably. But it does mean that even the most ordinary moment is built from the same physical principles that govern the stars. Of course, no good scientific idea remains untroubled forever, and general relativity is no exception. It is one of the greatest theories ever made, but it is not the final word on everything. It does not sit comfortably beside quantum mechanics in all circumstances. It encounters deep difficulties when we try to describe the universe at the smallest scales and the strongest curvatures together. Black holes and the earliest moments of the cosmos still pose questions that push the theory toward its limits. So when we say gravity is geometry, we should not imagine that all mysteries have been settled and the matter is closed for good. Physics is not a cupboard one reaches the back of. It is more like a house in which every opened door reveals 3 more, and at least one of them leads somewhere with unreasonable algebra. Still, the fact that questions remain does not weaken what general relativity has already taught us. If anything, it makes the lesson more impressive. To discover that gravity is not fundamentally a downward pull, but the geometry of space-time is already a dramatic enlargement of human understanding. Even if some deeper theory eventually tells us that space-time itself emerges from something more basic, Einstein's insight will remain one of the great turning points. He showed that what we had taken to be background was active. He showed that rest was not what we thought, that time was not what we thought, and that falling was not what we thought. Few intellectual achievements have rearranged so much with such economy. And there is a moral, if one wants to use that word gently, in the way this happened. The lesson is not merely that the universe is strange. We already suspected that. The lesson is that the familiar can conceal the profound. The floor under your feet feels ordinary because it is always there. The passing of time feels straightforward because you live within it. The night sky seems serene because the motions are slow compared with a human life. But science often advances by taking what appears too familiar to question and asking whether our first explanation is really the deepest one available. Gravity did not need to be abandoned as an everyday fact. It needed to be reinterpreted at a deeper level. The ordinary survived. The understanding changed. That sort of revision is not always comfortable. Human beings are fond of intuition, and understandably so. Intuition has practical value. It gets us through the day. But good physics has a habit of being less concerned with what feels natural than with what is true. Sometimes the world rewards intuition. Often enough it does not. Einstein's gravity is one of the great examples of that. No ordinary feeling tells you that the ground is pushing you away from your natural free-fall path. No everyday impression tells you that time runs differently at different heights. No casual glance at the sky tells you that light bends because space-time curves, and yet the evidence says all of it is so. there is also something almost tender in the fact that the deeper truth does not cancel the surface one. You can still say the Earth pulls things down. You can still catch a ball without discussing geodesics. You can still warn a child not to jump from something foolishly high without mentioning curved space-time. The older language remains useful because it captures the practical pattern. The deeper language becomes necessary when precision, unification, and understanding demand more. In that sense, science does not always replace common sense so much as place it within a larger frame. That larger frame also changes how we think about ourselves physically. We are not creatures hovering against gravity in some absolute sense. We are bodies living within a curved space-time environment, supported by surfaces, guided by geometry, and measured by clocks that participate in the same structure they record. The body feels weight because it feels support. The mind experiences time because it lives along a world line in a geometry shaped by mass and energy. Even memory and planning, which feel so inward and personal, unfold in a universe whose structure is far less simple than our ancestors could have imagined. And yet, for all that complexity, the result is not alienation. At least it need not be. One could look at relativity and conclude that the world is too strange to feel at home in. Or one could take the opposite view, that understanding the hidden structure of the world is one of the ways we become more at home in it, not because it becomes simpler, but because it becomes more honest. The earth under your feet is not a flat passive stage. The sky above you is not a decorative dome. Gravity is not just a pull. The more accurately we see these things, the more fully we inhabit the reality we were born into. So what does it mean for us that gravity is geometry? It means that the world is more unified than it first appears. It means that matter and motion, light and time, floors and planets, clocks and galaxies all belong to one connected structure. It means that free fall is natural, that support is what produces weight, that time is shaped by mass, and that the universe is built not merely from things, but from relationships between things and the space-time they inhabit. It means that the common image of reality as objects moving around inside a fixed container is too simple. The container itself is alive to what it contains. It also means perhaps that reality is more patient than we are. Gravity does not announce its deepest nature loudly. It lets generations live with a useful half-truth before revealing the fuller picture through careful thought and careful measurement. It lets apples fall and planets orbit for centuries before someone notices that standing still is more peculiar than it looks. It allows clocks to disagree quietly until our technology becomes refined enough to care. It bends light by tiny amounts and waits for an eclipse and a set of instruments and a very determined species to notice. And maybe there is something fitting in that. The universe rarely hands over its structure in one dramatic flourish. It reveals itself in layers, a familiar fact, a better explanation, a strange consequence, a new measurement, another revision of what counts as obvious. Gravity began as the thing that made stones fall, then it became a universal attraction, then it became geometry. Perhaps one day it will become something stranger still, but even now, at this stage of the story, it has already taught us something lasting. That reality does not owe us simplicity, but it often rewards patience. So the next time you set down a cup, or feel your feet on the pavement, or watch the moon hanging quietly above a roofline, it may be worth remembering that none of it is quite as plain as it seems. The cup rests because a table pushes upward. Your body stands because the ground keeps you from free fall. The moon moves as it does because space-time around the Earth is shaped in a particular way. And all of it, from the kitchen to the cosmos, belongs to one shared geometry that we are still learning how to describe with sufficient honesty, which is, I think, a rather good place to leave the mind for now. Not with the old certainty that gravity is just a pull and the matter ends there, but with the quieter and a more interesting recognition that the world beneath us is structured more deeply than it first appears, and that even the simple act of standing still turns out to be part of a much larger conversation between matter, motion, time, and the shape of reality itself.